So let me record this. So very near and very dear to your heart, to your mind, and your rest of your body. And that is going to be our friend water and a sweet Boston accent, and then air. I don't think you really can say air, maybe air. Air, there you go, probably in a Boston accent. So let's dive into water first, because clearly, super important topic, very much in line with sort of a lot of woes that we're seeing in today. So let's talk about water. Let's talk about what water, ecosystems in water. Let's talk about pollution of water, and so on and so forth. So we're going to start with this quote from Mr. Benjamin Franklin. And Ben Franklin says, "We know the value of water when the well runs dry." And I think that's a pretty dang good quote from Ben Franklin. I mean, he was a pretty smart dude. Obviously he was involved with the founding of this country and all that stuff. But Ben Franklin, like sort of many of the people that founded this country, had a lot of foresight about sort of future issues, even though they were back in the 1700s. And I really think this quote from Ben Franklin really hits home, because we can sort of transition from that quote and think about, well, let's get you guys thinking about your own personal lives. Have you ever worried about water quality? Have you ever worried about your accessibility to water? Has anybody ever worried about those things? You don't need to tell me. I'm not looking for you to tell me, because that seems like a sad thing. But you're sort of thinking about that, like in context of Ben Franklin's quote, like, have you ever, just reflect yourself. Have you ever worried about water? Have you worried about the quality? Have you ever worried that you're going to turn on the tap that's going to come out brown? Maybe if you have well water, you worried about it coming out brown, because I remember that when I was a kid. But have you ever worried about water like, say, the people in Africa have? Or have you ever worried about water in the context of, say, people in Flint, Michigan, right, where they have basically had lead in their water every day for the past, nearly a decade, in that ballpark. So and then the other question you could sort of think about as an extension of that is, how much water do you use on a daily basis? How much water do you think you waste on a daily basis? Is there something you could do better with your water your water habits? So what, sort of keep these ideas bouncing around in the back of your head. What does water mean to you? I mean, obviously it means a lot to you, because you are about 70% water. But what does it mean? Do you ever think about water? Do you ever consider water when you're doing anything? So just sort of keep those ideas bouncing around in the back of your head. Now, give us some context for some of the things we're going to talk about. About the average American, and Americans are usually at the high end of usage. Just as a note, pretty much everything we're going to talk about, you'll see that Americans are kind of way up there in the rankings of overuse of things. But the typical American uses between 80 and 100 gallons of water daily. Now you might think to yourself, there's no way any human drinks 80 to 100 gallons of water or uses 80 to 100 gallons of water on dishes or showers. And you'd be right about that. Right? 80 to 100 gallons of water is a massive amount of water. So just to put that in perspective, 100 gallons of water is 800 pounds of water. So it's a huge amount of water. You're talking about like bathtubs and bathtubs full of water. But how does the average human use that much water here in the United States on a daily basis? So we're going to get into that in a second. But again, keep that idea bouncing in the back of your head. And then to sort of give us this really diametric opposition to that is where we have about 3.5 million people every year globally die as a result of contaminated water. This can be something as, is simple as like there was just like a cholera outbreak, right? Like we saw after the 2015 earthquakes in Haiti, right? That's one type of contamination. But you could also think of maybe there's pesticides or other chemicals hanging around in the water. So lots of people die every year, unnecessary deaths from contaminated water. But that's just contaminated water. A significantly higher proportion of people die simply because they lack access to enough water. And about 20% or about 1/5 of the world's population does suffer from water scarcity on a daily basis. So kind of two really diametrically opposed points here, right? Lots of consumption here in the United States. Other places in the world, some pretty severe lack of consumption. So let's think about this like sort of in a special case. Now we're going to migrate over to Africa for this case, but we're going to go down to the bottom of South Africa. In South Africa, we're going to talk about Cape Town in South Africa. So, not super reflective of what Africa is like as a continent, just because Cape Town is, is much more developed than, most of sub-Saharan Africa. But Cape Town has about 4 million people or so in it. And during a few years ago, they actually suffered about a 3-year drought, which actually reduced their water reservoir capacity by about 75%. So they're down to 25% overall capacity. And that's pretty dramatic. Like losing 75% of water is again, really, really dramatic. So I know 25% might seem like a lot of like a reservoir, but given how much water we use, that's a lot of water loss. Now, in 2018, the South African and Cape Town officials there warned that if they let water levels drop below 14%, the government would actually manually shut off residential and ration about 6.5 gallons of water per person per day, which is kind of it's an extreme reaction, don't get me wrong, but it's kind of a reaction that you kind of have to make, right? And you'll see why that's the case very, very shortly as we sort of talk about how water is cycled through this planet. And thankfully, the residents of Cape Town actually responded by reducing their usage by about 50% to about 10 gallons per person per day, avoiding this governmental control of their water system, avoiding shutoffs and rationing. So Cape Town, South Africa, a pretty good case of lots of consumption of water, leading to water scarcity, leading to potentially dire governmental actions, but leading to people recognizing the problem and fixing the problem, which is, I think, a pretty good success story. I wish we could see this success story with a lot of different environmental issues out there, but at least we saw it in this one case, which is good. So let's talk about water. Now, one aspect of your average everyday water use is what we call embedded water. And you might never have heard this term before, or you might have sort of thought about it at some point, but embedded water simply refers to water that is used to produce the goods that you consume. So and it's kind of a interesting thing because it does vary pretty heavily. So we can see this handy dandy chart over here. I really like this chart because it really sort of tells you sort of how your consumption habits are affecting how much water essentially you are using in addition to the water you're using for bathing and washing your clothes and dishes and stuff like that. So you can see coffee ranks at the top at about 18,000 liters, or about 132 liters per 1 cup of coffee. So I'm giving this lecture. I have a cup of coffee. It's about 150 milliliters, which means it took 132 liters to produce this 1 cup of coffee, which is kind of a sad thing to think about when you're drinking coffee, but it is what it is. We see chocolate requires about 1,700 liters per about a 3.5 ounce bar. So like a Hershey's bar, lots and lots of water. You can see beef is about 15,000 liters per kilogram produced. So lots of beef. So if you eat 2.2 pounds of beef, it required 15,000 liters of water to produce that 2.2 pounds of beef. And then we sort of go down, right? Cotton to make our clothes, 8,000 liters per pair of jeans, tea, pork, chicken, rice, so on and so forth. And then we get down to the bottom where we see something like potatoes, where to produce a kilogram, and a kilogram is about 2.2 pounds, is about 287 liters of water. So lots and lots of different water uses, different crops, different products require different amounts of water. And this is just like to grow these things, right? This doesn't include like processing or cleaning or anything else that's involved with the production of anything. So this is, again, just to grow these things. And I think the one thing I think is kind of funny about this, in my other class pointed this out because they're just one day ahead of you guys, is that the main takeaway from this graph is yes, we use a lot of water, but in the most college-esque takeaway, that you should really be drinking more beer, because beer is much more water friendly than coffee. So that's the thing you take away from this graph, according to my other class. So I thought that was kind of funny. And my wife is shaking her head at me like I'm saying something that's super nerdy. And I kind of agree with her, but I thought it was funny at the time. So your background water use, i.e. your embedded water use, does vary based upon your diet, as well as your other consumption patterns, including textiles, drinks, and so on and so forth. Now, let's talk about where our water is, because it's really It's really dramatic. Now, your average everyday person across the globe, and will vary depending on where you are, your average human loses about 2 to 3 liters of water, and this is via sweat. Exhaling of water vapor. So I'm sure you guys know when you talk, you do spit water, but your breath is hot and heavy, and that's because of water vapor. So gaseous water, and we'll talk about that soon. And then waste excretion, your pees and your poops. So we lose about 2 to 3 liters of water every day, which is why people typically recommend you drink like half a gallon of water or so on an average everyday basis, because you lose a decent amount of water. Now, clearly this 2 to 3 liters of water is, it's on the low side. There's people who lose way more than 2 to 3 liters of water every day. But again, on average, 2 to 3. So let's look at where our water breaks down. In this graph, I really love this figure because it really gets at the proportions really nicely, though I would change it a little bit, but that's beyond the point. But you can see that of all the water on the planet, 96.5% or 97.5% is salty. So it basically means it's inaccessible to you as a land-faring individual. So 97.5% is either in the ocean or in other salt water. Now you might ask, what is other salt water? For those of you that have been to Utah, the salt lakes out there, that's other salt water. If you've ever potentially heard of the Dead Sea or been to the Dead Sea is a saltwater lake, very, very salty. Again, that's other salt water. So there are other reservoirs of salt water outside of our friend, the big blue ocean. And then of that, the remainder, 2.5% is fresh water. Now, when we break that fresh water down, because that's what we can consume, that's what we have access to, that's what we use to water our crops, feed our, to give our chickens and cows water. 69 or about 70% of our fresh water is found in ice caps, snow, and permafrost, and glaciers. So places that are very, very cold, and very much like the saltwater in the ocean, most of this stuff is just inaccessible. We basically can't access most of the stuff that's frozen in the Arctic. Just basically not feasible at this given time. So lots of our planet, 70% of 2.5%. So let's pretend we're at, 98.5% of all water is simply inaccessible to humans, which is a lot of the water on the planet. Now, let's look at the other percentage. So we have 30% is groundwater. This is water that is tucked underground in reservoirs and things like that. Some of this is accessible. So if you have well water, for instance, well water is tapping into groundwater. And then other freshwater sources, which is about 0.4% of this 2.5% chunk. So it's, fractions of a percent of the total global water supply. 67% is found in lakes, 7.7% in swamps, 13% is just directly trapped in soil, so it's inaccessible. Swamps are also relatively inaccessible for water. Lakes are clearly accessible for water, so that's cool. 10% of that is water vapor in the atmosphere, so gaseous water hanging around in clouds. 1.5% is in rivers and streams. And then 0.8% is water living in organisms, or I'm sorry, water in living organisms. So of all these water sources, we can access groundwater, lakes, and rivers and streams, and that's about it. So of all these things, we access a fraction of a percent of the available water on this planet, which is really remarkable when you sort of think about how much water there is on this planet, right? A fraction of a percent. So this is where our water is. I hope you found that little bit interesting. I always think the decrease in proportion of available water is really fascinating, no matter how many times I look at a figure like this. So let's talk a little bit about sort of the connectivity of water. So we'll talk about what's called the hydrosphere, or sometimes just simply called the water cycle. Because water is not static. You guys have all seen pictures of Niagara Falls, right? You've seen running rivers, right? You've seen the ocean's tides. Water is not static, so water moves quite a bit. And everyone has seen precipitation, right? Everyone has seen rain or sleet or snow, or hail. If you live in like the southern states, you've seen monster hail, which is always kind of cool. So lots and lots of water on the planet, clearly. It's all connected in some way, shape, or form. Many of you might have heard the old saying, all rivers lead to the ocean. And that's simply a nautical thing, but it's also a really handy thing of everything is really connected in the water cycle. And it doesn't really matter where you are, it's connected in some way, shape, or form. So now, what happens to our water? Well, if it's hanging out and it's accessible on land, so it's like in a river, it's in the soil, it's in a lake, it's accessible to the sun. So what the sun does, and I'm sure you guys probably already know this, but we're just going to go through it again. The sun heats up the water, causes the water to evaporate, becoming water vapor, and that water vapor goes into the atmosphere, hangs around, eventually forming rain clouds, and then raining, snowing, sleeting, or hailing down onto the planet. Fun fact about rain clouds, they are actually seeded by our microorganisms. So bacteria and fungi get fluffed up into the atmosphere via the ocean, and they actually help start rain clouds. So it's kind of a really cool thing. I don't know if anyone's ever heard that before, but I always find it fascinating, so I like to tell people about it. So that's sort of our flow of water from the land up into the atmosphere. And the reality is rain and snow and sleet or whatever, they can occur anywhere on the planet. But the reality of it, because the ocean is so big, 75% of all precipitation does fall into the ocean. So even if we evaporate water from a river, it's most likely to end up back into the ocean, just the way it is. Now, the reality is once something makes it into the ocean, it actually hangs around the ocean for a very, 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 very long time. So the ocean water has about a average residence time of about 3,000 years. Now, residence time simply refers to how long that water is hanging around in a given area. So for the oceanic water, it hangs around for thousands of years. So the water that's in our oceans, much of it is as old as it was, back when they were building the pyramids, right? When there was, pharaohs and stuff like that walking around in Egypt. So our water in our ocean hangs around for a very, very, very long time. Now, of the water that falls onto the land, a lot of it will simply seep into the ground and hang around in the soil. A lot of it will make it into streams and eventually make it to rivers and lakes and eventually into the ocean. But a lot of water, when it rains, it will seep through our soil, through what we call bedrock. Now, bedrock is simply just underground rocks. It's really all that you need to know about it. And then that, as it sort of seeps through the soil, it eventually makes it to what we call aquifers. And aquifers are simply underground water. You can think of them like ponds or lakes. They're simply underground areas where water collects. If you have well water, as you can sort of see in this picture, you tap into aquifers, i.e. underground water, to get your water. So just as a note. But again, this is sort of our connectivity here, right? It evaporates, it rains, it seeps into our rivers, it seeps back underground, or it goes into the ocean. But again, all this area is connected in some way, shape, or form. Now, the last thing I'd like to make mention about these aquifers or groundwater is that they move very, very slowly. So water, as it moves through our soils and rock and stuff like that, it moves only about a foot per year. So like, if you put a drop of water and the drop of water moved a foot through the ground, that would take an entire year. So that's just to sort of put that in perspective. Groundwater moves very, very slowly overall. Now let's look at the water cycle, sort of summarizing a lot of the things I just said, but really, really handy figure. I like this figure quite a bit. But again, we have evaporation leading to water vapor and then precipitation. Most of the precipitation lands on the ocean. Some of it lands on our land. Some of it collects in glaciers and ice caps where it kind of hangs around. Other of it runs off, goes into rivers and lakes and streams. A lot of it percolates through the ground. A lot of it absorbs in the soil. But this is our water cycle. Again, pretty dang connected network of movement of water on this planet. And I think sort of, as we'll see when we start to look at oceanic currents in a few slides, you'll see that the water cycle is really, really connected. I think it's pretty cool to sort of think about, like, sometimes if you take a drink, it might have come from the ocean, right? Evaporated water from the ocean, or it might have come from a glacier, or it might have come from rain. So there's all potential sources for where your water comes from. Now, I want to just make mention of a cool ecosystem. It's because it's a lot ecosystem people don't hear about too often, but there's a whole group of ecosystems called groundwater dependent ecosystems. So basically aquifers or caves where there's lots of underground water. They're not sterile environments. They have rich communities of bacteria and other microorganisms, but they also have all sorts of cool and wacky and wild animals like this. So we have this little crustacean here. Its genus species is Nymphargus aquilex. That's what it's called. It's, as you can see, its body is completely translucent. Now, you might say, why is it translucent? I mean, it looks cool, obviously, but when you live in a cave, when there's no sunlight, you don't need to have pigmentation in your skin. You simply don't. And so organisms that live in these groundwater dependent ecosystems, i.e. underground where there's no sun, have some pretty cool evolutionary adaptations. So they start to look like this. They start to look colorless. It's a pretty cool thing. So you can have life completely underground, supported solely by groundwater. If you want to know a little bit more about these cool groundwater communities, there's during Planet Earth, if you guys ever saw that series from BBC, they actually have a whole 15-minute spiel about these cool underground communities that I recommend taking a peek at. Now, there's also some interesting things that we see in Africa and elsewhere, but they're pretty common in Africa, as you can sort of depict from this picture, where we have groundwater seeping back up into the surface. And so you can see this little pond here. It's groundwater that seeps back up, providing a vital water source to this very, very barren area of the sub-Saharan prairie. So groundwater, it's not just hanging around out there doing nothing. It really is connected and really does support ecosystems, whether or not we think it or not. So our sort of biggest reservoir of fresh water that's at least accessible to humans and most life on the planet is lakes and ponds. Now, you might ask yourself, how do we get a lake and pond? Well, there's three mechanisms by lakes, the way lakes and ponds form. So the first one is actually what happened with the Great Lakes here in the United States and Canada. Now, the Great Lakes, as you guys probably know, they are incredibly large. For instance, like when I was living in Michigan, my wife and I went to Lake Michigan, and Lake Michigan is so big. It has, which is, what separates Illinois and Wisconsin from Michigan here. It's so big, it has its own waves. And it's not just because there's boats and stuff. It's so big, wave action actually occurs on these lakes. So these lakes are no joke big. If you've never been or never really thought about the Great Lakes, they are truly monstrous. They're also very, very cold. So if you don't like cold water, not the best place to go. But anyways, these Great Lakes actually formed as a result of glaciers. So as you guys probably have heard, we have ice ages where large glaciers cover a decent chunk of the planet. And so as the ice ages come to end, these glaciers start to retreat. As the glaciers start to retreat, they gouge out parts of the land. And if you have a big enough set of glaciers, you can gouge out monstrous holes like you see here for all of our 5 Great Lakes. So one of the primary mechanisms by which we create lakes is glaciers. Now, that's not something that's happening right now because we don't have big enough glaciers to do that. But in prehistoric times, that's how these Great Lakes formed, and it's how many of the great northern lakes in, say, Russia or Scandinavia and so on and so forth formed as a result of retreating glaciers. So that's one mechanism. The other mechanism is probably a cooler one, is asteroids and comets. When they hit the planet, they essentially create big holes, as you can see here in Crater Lake in Oregon. And when you have a big hole, as we do with the Great Lakes, water will start to collect in it, thus creating a lake or a pond. So kind of a cool thing. And then the final thing is actually what we call oxbows, or oxbow lakes. Now, as rivers are flowing, and we'll talk about rivers soon, they start to erode sediment and other structures along their banks. So some rivers oftentimes get wider. So for instance, the Mississippi River was much more narrow before it started eroding the banks and became much, much wider over time. So what ends up happening, you get this erosion, and as you erode, you create new water flows. And sometimes these water flows will actually essentially cause changes in the way the river flows. And as the river sort of like diverts its path because of its erosion, you create these little mini oxbow lakes where you kind of have these places where the river used to flow and it's really, 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 really sort of carved out from the river, again, creating these lakes. So this is the way our lakes and ponds form. We have to gouge the earth, and then water collects. Just they all end up doing the same thing. Water pools somewhere, but they happen in three distinct mechanisms: glaciers, asteroids, and changes in rivers. Though I'll argue that the asteroid one is probably the coolest one because obviously asteroids are cool. So, all right. So our lakes and ponds, if you've never been in one, they support some pretty vibrant ecosystems. So we're going to talk a little bit about the ecology of ponds and lakes, and sort of the distinct zones that form as a result of sort of the geology. Hey, Joe, can you mute yourself, Bill? You're popping in every now and then. Thank you. And so we can look at a lake or a pond, and they're typically very still, right? You guys have probably seen a lake or a pond. They're still, right? They don't have a lot of movement into their water. And so when the water is very still, we call these lentic ecosystems. You don't really need to remember that, but that's just what they're called. And the cool thing that happens in ponds, and this is actually the same thing that happens in the ocean, is that as you go away from the land, you form some distinct areas. So the first area you get is what's called the littoral zone. And this is basically where it's shallow enough where you can support aquatic plants. And sort of have this nice living part. And then you move out to the deeper parts where you get what's called the pelagic zone, where basically it's too deep for plants to grow on the bottom. So you get photosynthetic algae and plankton and things like that growing in the surface. And then the bottom becomes relatively dark. It's referred to as the aphotic zone because there's basically no light. And basically, only thing that happens down there is when things die, they fall there and they're eaten by other things. So we have these three distinct zones: the littoral zone, and then the pelagic zone, which is divided into the photic zone, where photosynthesis occurs, and the aphotic zone, where photosynthesis simply does not occur, where basically things go to be eaten after they're dead. But you'll notice that both of these systems, whether it's the littoral zone or the pelagic zone, support vibrant fish communities, insects, and stuff like that. So they produce, again, very, very vibrant and very, very active communities essentially year round. We sort of think of here in New England as like when our ponds and lakes freeze over, it's all done. But underneath that ice, there's all sorts of stuff going on. So lakes are kind of always active. So that's our sort of breaking down of our lakes and ponds. Pretty cool systems. They get oftentimes quite stinky because they're stagnant water, but again, pretty cool systems nonetheless. Now, a lot of ponds and rivers are fed, ponds and lakes are fed by lakes and rivers and streams. And so that's going to be our next topic. And you can sort of see that flow here where we have a glacier. We have meltwater from the glacier feeding the river that goes all the way down until we get to, a stagnant body of water here or here. And so rivers are our next ecosystem we're going to talk about, and streams as well. But mostly think of this about rivers. Now, rivers and lakes, as you guys know, they have current to them, right? They can be fast or they can be slow, depending on where they are. And rivers and lakes are what we call low-tick ecosystems. And low-tick ecosystems are pretty cool because they have some pretty distinct habitats all along the way. Now, if a river or a stream is fed from a mountain or a glacier, as it goes down the gradient of the mountain, it's very, very steep. So I used to, when I was a kid, I used to go to Mount Washington with my family, and we used to go up to the White Mountains up there, and we used to go to these glacier-fed rivers, and the current would be super fast through these rivers. But you would then go downstream a bit when gravity has sort of lessened, and you can sort of see the rivers start to slow down. And that's one of the cool things about rivers. They can be very, very fast and then very, very slow right away as the gradient decreases or increases. So it's a pretty cool thing. Now, one thing we commonly see lakes and rivers is actually sort of small tributaries, very small streams that can feed into rivers or sometimes break off of rivers, creating all sorts of unique habitat. The other thing we commonly see is actually rivers will feed what we call wetlands. Now, wetlands are simply essentially permanently wet pieces of land. And so we could think of a couple examples of wetlands here where we have a marsh. You can sort of see the picture here. These are sort of permanently wet areas covered in grasses. So those are marshes. Now, if you have a permanently wet area that's covered in trees, this is what we call swamps. So there are two distinct types, marshes, with grass, swamps with trees. They are both collectively called wetlands, though. So just as a note. And then eventually you make it down because all rivers eventually flow to some large body of water. You make it down to the ocean. You see we get to what's called an estuary. Now, in areas of the world, like say here in New England, our estuaries are dominated at the coast by wetland areas called salt marshes. This is, as I think I mentioned in the first class, that's where I used to do my graduate work. So I love salt marshes. They're coastal, grassland, wetland ecosystems. But as we discussed in our ecosystem services class, mangroves are also coastal wetland ecosystems as well. So we have these coastal wetlands ecosystems, again, the interface between the land and the sea. And then we eventually get down into what's called an estuary, which is simply a coastal body of water. That's really it. So that's the sort of flow of a river, pretty dynamic, pretty cool. Now, let's talk about wetlands and estuaries because, I mean, they're awesome and I have a high love of both of these ecosystems, but let's talk about briefly. As I mentioned, wetlands are essentially permanently wet areas. They can be on the coast or they can be inland, but these areas, they might not seem like much. This might not seem like a cool thing or an important thing, but they are very, very important and very unique ecosystems. So just as a note, we like to think of wetlands as being stinky or whatever, but they are very, very important. And then we have estuaries, which you can think of Boston Harbor as a sort of an estuary. It's the interface between the land and the sea. Again, very, very important communities. If you like fish, for instance, or lobster or shellfish, estuaries are basically nurseries for most of the fish and things we eat. So just as a note, these are sort of our river, that's our flow, and it's sort of giving us some pretty unique ecosystems along the way. And again, our ponds and our streams also have some pretty unique ecosystems within them as well. So that's what we have. So let's sort of move on to the sort of the ecology of our freshwater. Let's move on to how we affect our freshwater. And we do this from a number of ways. We're pretty good at tampering with our freshwater, unfortunately. So how do we contaminate freshwater? Well, there's a number of different ways. If we think historically speaking, back here in New England, where our rivers used to run purple and green because we used to dump stuff in them, the primary mechanism by which we pollute our water is simply by either purposely or accidentally dumping things into our waterways. And then, as you guys probably know, we take water from our rivers, our lakes, and our ponds for our own drinking water, for our own feeding our own livestock, for washing our dishes and clothes and things like that. So humans can dump things directly in them, but sometimes if our water is perfectly fine, one of the common ways we actually can impact our freshwater is actually by our own infrastructure. So the example here we have is Flint. Because it's it's still a very timely issue, but it's also a really easy issue to understand. It's also a really easy issue to fix. They just, for whatever stupid Michigan reasons there have been, they have not done it. But the city of Flint, Michigan, it's a relatively poor region of Michigan. I mean, most of Michigan isn't doing too great economically, but Flint, Michigan is on the poorer side. And the people in Flint, Michigan get their water from the Flint River. They have a water treatment plant that draws water from the river, disinfects it, treats it a little bit, and then pipes it through to different communities. Now, the way they used to make pipes pre-1986 is they had these little pipes. They're copper pipes, and these copper pipes. Copper pipes. They're they're pipes made out of metal. Sorry. Blanking on the name, and these pipes are connected by copper, and they're essentially soldered to the copper soldered to the metal pipe by lead. And so you guys probably know lead is a no joke heavy metal. I'm sure many of you probably already know what's going on in Michigan, so this might be a little refresher, but lead is a no joke thing. It doesn't really affect adults very much, but lead is neurotoxic. And so if you're a developing child, getting lead into your system is kind of a bad thing. So what's happening in Flint, Michigan is these little lead pieces are actually decomposing. They're breaking down because the water in the river is kind of corrosive. Most fresh water, as we'll talk about, is a little bit acidic. And so the acidity of the water corrodes the pipes, corrodes the lead, allows lead to flood into the drinking water of people, thus contaminating the drinking water of Flint. So we have two distinct ways we can poison our own water, our own infrastructure, or we just dump things into our river. Both are equally as common. Just as a note, our infrastructure is oftentimes really, really, really bad. So both are pretty common, unfortunately. So that's one way we affect our water. But one of the actual other ways we affect our water is simply by just taking a lot of it. That's something we do pretty damn good. So we're going to look at actually the Agala, I believe that's how you pronounce it, aquifer. Now, as you notice, this underground piece of water spans New Mexico, Texas, Oklahoma, Kansas, Colorado, Nebraska, North Dakota, as well as Wyoming. It is a monstrous underground piece of water. It really is. You know, if to put that in perspective, that'd be like, as an underground piece of water, it's like the size of like Lake Michigan. It's huge. So this is a no joke aquifer. Now, one of the sort of reasons we care about underground water sources is because we rely pretty heavily on them. So where I grew up in central Massachusetts, the entire town pretty much of Hudson, Massachusetts had well water. And as I mentioned, well water allows us access to underground aquifers. So we have this entire area of the country, and it's, as you guys probably know, it's pretty heavy in agriculture. Nebraska grows a crap ton of corn. But as we sort of expanded our technology, we've got pretty heavy access to a lot of this groundwater here. And as you sort of see from this figure here, and I think it does a pretty good job, we're doing what's called water mining, essentially. We're withdrawing large amounts of water from this aquifer for our drinking water, for our crops, for our livestock, for our dishes, whatever you want to think. And you can sort of see this aquifer. It's pretty much all red here in this bottom part, where the population density is a little bit higher. Our friends in Denver are about here, so it's a relatively large city. And you can sort of see most of it. We've seen a pretty sharp decline in the water resources, right? So in this area of Texas and up into Kansas and Oklahoma, pretty heavy taking of water. And so the reality of this is we are affecting our water systems by just taking a lot from them. And so this is an aquifer. Now, aquifers take a very, very long time to sort of fill back up as you drain them. So they are what we would call a renewable source, but they renew on a very, very, very slow time period. So for instance, this aquifer takes about 10,000 years to completely refill. And we're draining it at a rate much faster than the rate by which it can refill itself. Now, this is sort of an easy to grasp example, I think, but the Mississippi River also provides a nice, easy example. But you can see the Mississippi River is actually at all-time lows right now because of increased withdrawal from farmers all along it, again, leading to the Mississippi River being a depleted water source for the Midwest and sort of our breadbasket of the United States. So two distinct ways we can affect our water, taking a lot of it, and then essentially poisoning it in some way, shape, or form. Now, the reality is that this sort of situation we're seeing here is actually so dramatic, you can actually see its effects on the topology, i.e. the vertical space of San Joaquin Valley, California. And so you can see this picture here because they've taken, and you guys probably know this, California is a pretty heavy agricultural state for many, many important cash crops. But they take so much water for their crops, it's actually led to a decline in the height of their land. So you can see this gentleman here, or actually, sorry, I think it's a girl. I don't know. It's kind of too small for me to tell. I can't remember who it is. But you can see this, the height of the land used to be up here in 1965. And after 48 years in 2013, the height of the land has dropped by 7.3 feet. Now you might ask yourself, why is that the case? Well, as we draw more and more water, the water is essentially keeping the land essentially up higher. And as you draw a lot of water or you draw too much water, it causes your land to sort of sink down into it. So it's pretty dramatic. You sort of can see this this effects on the San Joaquin Valley in California. Again, 7.3 feet of vertical height loss just because of taking water from aquifers. So again, I think it's pretty wild sort of visualization of how much water we physically take. Now, one of the other ways we can take water and affect our water is actually disruption of our water. And so we do this in a couple different ways. So the one you guys are probably most familiar with is dams. As we dam our water, it causes water to pool up and changes the flow of rivers and things like that, leading to some pretty dramatic changes. So, for instance, we have Lake Powell here. It's an artificial lake from the Colorado River, completely as a result of this very, very large dam here. So that's one way. Now, the other thing we can do is actually divert our water. And so, for instance, this is a canal in Colorado. So we can basically divert our water to allow us better access to it or potentially allow boats to go through. For those of you that have ever been down to the Cape Cod Canal is a great example of this, as is the Erie Canal up in New York. Again, diverting water to make things either better for us or allow us for better transportation. And then the final thing is actually we can do two things. They're the same thing, but two slightly different ways. We create what's called hard surfaces. And so one hard surface is we pipe things through tunnels. So that's one hard surface we can create. And the other hard surfaces we can create are driveways, rooftops, roads, and parking lots, which basically change the way water naturally flows. So we love to change disruption to surface waters. That's what we do. We do it really, really well for a variety of different reasons, right? Electricity, transportation, movement of water. We do a lot of different things to change our water. Now, the other thing we do when we change our water is we actually change what's called erosion. So as we change how fast the water flows or where the water flows, we change how the water essentially cuts through the land, how it erodes, how it moves sediment down. And that's kind of a big deal for a lot of ecosystems. We won't talk too much about it, but I just want to make mention of that idea. Again, just because it's a sort of an important thing. And again, we sort of disruptions to surface waters here, man-made canals like the Cape Cod Canal or this river here, pretty dramatic changes to our ecosystems. Pretty dramatic changes to the way our water flows. So we're going to talk about this idea a bit more, water pollution, later in the semester when we talk about waste. But I want to make mention of water pollution, and in particular, a couple different distinct types of water pollution. Now, we have two distinct types of sources of water pollution. The first is what we call a point source pollution. Now, this is basically where we have a pollutant, such as a heavy metal, and we know exactly where it's coming from. So in the case of here, we have some factory, it's producing some sort of pollution, and we know exactly where that pollutant is coming from. So this is what we would call a point source pollution, because we know exactly where it's coming from. Now, this is a contrast to a non-point source solution, such as urban runoff, where we have a pollutant, but we have no idea where it's coming from, or it has many, many sources. So we could think of like wastewater is a great example of this. If we pretend we have a pollutant in our waterways of wastewater, it has the potential to come from any number of these houses or buildings here. So again, it's a pollutant, but we don't quite know exactly where it's coming from. Thus, it's a non-point source pollutant. And now, water can be polluted in sort of three distinct ways. We have chemical pollutants. The case in Flint, Michigan with the lead, that's a chemical pollutant, but it can also be put into our waterways by agriculture, as well as like factories, as well as wastewater treatment plants and stuff like that. We have sediment pollution, which is pretty common, where basically lots and lots of loose soil gets into our waterways. Now, you might not think that's like that's a pollution, but too much sediment means that not a lot of sun gets to the water, which means plants and algae and things like that simply can't grow. And they're really kind of the bedrock of our ecosystem services, right? So if those things are shut down because of sediment pollution, ecosystems aren't doing too well. And then finally, we have biological pollutants. These are pretty common from wastewater plants. They're also pretty common from agricultural, but these are bacteria, viruses, fungi, pathogenic ones that make it out and cause havoc to those that are drinking it or to the animals there. So that's how we pollute our water. That's how water goes. Now let's talk about access to fresh water. Now, numerically, about 1/7 of the planet suffer from water scarcity on Earth. The vast majority of this does occur in poorer regions of the world. So for instance, areas of Africa, such as Mali or Niger, about half of the population of those areas lacks access to safe water. So water access is not uniform across the planet. I mean, that's probably something you guys already know. I mean, that's pretty common knowledge. Water is while a vital resource, is a unequally distributed resource, unfortunately. Now, I'm sure you guys have all probably seen scenes like this where you have folks in Africa walking hours and hours and hours in their with dilapidated plastic containers to collect water, to carry, right? And so the weird thing, well, maybe not the weird thing, but the thing you sort of see in Africa, which I think really highlights how awful this sort of thing is that you have this scenario here where people are carrying water, and it's typically women in Africa. And then in sort of in Cape Town, you have sort of this, South Africa, you have these sort of wealthier citizens constructing water tanks and stuff like that, to sort of get around this problem of access to water. So again, water access is again unequally distributed, and it sort of dramatically impacts the poorest the most. I mean, most things affect the poor most anyway, so that's not overly surprising. And so I sort of like to think about our access to water, and I think it's kind of a cool thing. So I had cereal for breakfast this morning. I had some Lucky Charms, because that's one of my favorite cereals. I'm sure you guys have all had Lucky Charms before. They're awesome. But I when I was a kid, I used to drink cow milk. But as I've sort of transitioned to an adult, I've moved away from cow milk because I just don't like it. And I've switched to almond milk. That's the sort of milk I've settled on because I think it's tastiest. And so many Americans like myself and those across the planet use plant-based milks, though if you ask the dairy industry, they are not truly milks, they are beverages. But I will never call almond milk almond beverage because that is simply just sounds weird. And so we have these alternative milks. And as we sort of showed in the beginning of this class, we have some pretty distinct water usage depending on the crop or the organism you're trying to grow. And so we can see here we have a glass of soy milk. For 1 glass of soy milk, it takes about 9 gallons of water. For 1 glass of almond milk, it requires about 23 gallons of water. And then 1 glass of milk for cow milk, doesn't matter like if it's whole or whatever, about 30 gallons. 1 yogurt takes about 35 gallons, and 1 Greek yogurt, which I will argue is the best of all the yogurts, takes about 90 gallons of water. So pretty distinct amounts of water required. Now, you have to remember for a glass of soy milk, it's in almond milk, it requires water to grow the plants. It also requires water to process the nuts and the seeds to make these things. So sort of a double-edged sword here. And then we have cow milk, which simply requires a crap ton of water to feed the cows, as well as to feed the plants that feed the cows. So lots and lots of water that goes in here. Now, you might ask yourself, why are we talking about this? Well, we're talking about water scarcity, right? And so we think about a situation like California, which has a massive almond growing operation there. We can think about all the droughts that have occurred in California because of how much sort of almond milk that's produced from California. It's actually led to some pretty scarce water scarcity in California. Again, just trying to produce lots and lots of almonds for things like almond milk, and lots and lots of cows to produce things like milk and cheese. So our sort of the point of this little detour here was to sort of show you that it's not just places like Africa that suffer from water scarcity. It's everywhere. But here in the places like the United States, it's oftentimes our choices that lead to these water scarcities, our sort of business models, as opposed to places like Africa, which simply just have a combination of poor infrastructure as well as just very little amounts of water. So now global water scarcity is a really sort of kind of an easy thing to sort of pin down as to why it's an issue. The reality is 90% of all of the water that humans draw upon goes to either agriculture, so watering our crops, so 70%, and then 20% is used for industry. Water is a great coolant, so they use it in factories and stuff like that. So we have this sort of pretty heavy use of just growing food in our industries, i.e. our economic institutes, for using water, again, leading to water scarcity. And then only about 10% of our global water usages as a species leads to actually goes into our mouths and our clothes and things like that. So lots and lots and lots of usages. Now, if you ever wanted to know how much water we use, it's a lot. It's hundreds of billions of gallons every year. But just to sort of give you a staggering number, given 10% is only used for residential, just to sort of put that in sort of perspective here, about 12.8 billion gallons of water isn't actually drank as in terms of like comes into a pipe. 12.8 billion gallons is actually just bottled and sold and shipped around the world. So just astronomically high amounts of water is bottled and sold. So again, thinking about your water choices, this is kind of a wild thing. Your food choices matter in terms of water usage. Now, so let's talk about water shortages, because again, water scarcity is not just a thing here in the United States. It's also a big thing elsewhere in Europe and in Asia. It's everywhere. So we can look at some pretty distinct drought map here. So this is from January 8th, 2019. So you guys probably remember in 2019, as pretty much every year in the past 5 years, California had really big wildfires. And that was very much true in January of 2019. And now what's driving the California wildfires? Or not just California, but also Washington and Oregon. It's really drought. That's really what's driving things. It's drought linked to climate change, and we'll talk about that in the climate change lecture. But you can see here, huge parts of the Midwest, Texas, a huge chunk of Florida, as well as here in New England, suffered from some pretty serious droughts. Again, this is just January 8th, 2019. That's just a figure I pulled. But you can look at this map pretty much any time during the year, and there's spots throughout the United States, there's spots throughout the planet that have drought of some shape or form. So our drought is in turn, so all these droughts, i.e. a lack of rainfall, is leading also to our water shortages as well. That was the sort of the point here. And again, it's pretty concentrated here in the West, but again, it affects the planet as a whole. Now, just to give you some local information, the state of Massachusetts was basically in like a 5-year drought from about 2014 all the way up to 2019. And we were actually in a pretty severe drought earlier this year. But for those of you that live in Massachusetts know that we've gotten some pretty heavy rains this year. For instance, like last night, we got a pretty big deluge of about 1.5 inches. At least here where I live in Easton. So that's actually helped get rid of our drought here in Massachusetts. But again, drought leads to water shortages. And that's not just true here in Massachusetts, it's true elsewhere in the United States as well as globally. Now we can ask the question, is there anything we potentially could do? Well, one of the big things is actually water conservation. So one of the problems that we have is that we use a lot of water for crops and things like that, but a lot of the water from our usages as individuals can actually be done and recycled. So we could potentially take fresh water that, say, our wastewater, and treat it, or water that goes down your sink, treat it, and then basically repurpose that water in some way, shape, or form. Now there is some pretty cool places that are doing this. So for instance, in Monterey County, California, they have this really cool thing where they take wastewater from local communities, they treat it, and they pipe that recycled water out to the plant, to these farm areas here in blue, to potentially use that wastewater for another purpose. Because otherwise that wastewater would simply just go into the ocean and be lost to our things. Now, one of the other ways that we've actually can help essentially mitigate water scarcity, and there's a couple ways. Now, dams are great. Dams, either natural because of like beavers, or dams because we've built them, are great ways to provide a constant water source. But actually, one of the cool things we see is actually these really fascinating rainwater harvests. Now, these rainwater harvests, sorry, my dog is trying to climb on top of me. These rainwater harvests can be as simple as I have a barrel and I collect rainwater to use, or they can be slightly more complex where you have these little wells that you find in a couple different places around the world. But basically they collect water underground. The water stays cool, but it provides a consistent access of water that it can be pumped up. So we can either do dams, we could do cool things like this, or we can actually desalinate water. So we take oceanic water or water from ponds and stuff like that that are salty, and we pull the salt out of it. Now, desalination sounds awesome, but desalination at the moment is not really particularly easy to do, nor is it climate change friendly. It requires an immense amount of energy to desalinate water at the given time. So while it provides a lot of hope for the future, desalination is not really where it's at right now. So, but definitely as water scarcity becomes a bigger deal, desalination is going to have to become a much, much more important thing. So just as a note. Now, How do we keep our fresh water clean? Well, wastewater treatment and treatment of agricultural as well as industrial products is the way to go. So, for instance, we can look here of a sort of a typical wastewater treatment plant here in the United States, where we have multi-chambered systems where wastewater enters, we separate out big particles, and then we essentially pipe it through a bunch of different systems to let bacteria start to eat the things, to separate out large solids, eventually treating them with some sort of chemical such as ozone or chlorine, leading to clean water making it out, and clean water potentially being used for something else. So that's commonly what we do here in the United States and in Europe, but globally, about 2.5 billion people simply don't have access to a way to treat their wastewater. So you could think about a place. I had a student last semester that was from Haiti, and in where she grew up. Actually, the way that they would go to the bathroom, she was telling me this when we were sort of going through this, that most people just go to the bathroom like like their bathroom actually just drops, the wastewater actually drops straight down into the rivers, and then it's just flushed out to the ocean. So again, we can see something even in our own Western hemisphere, not really having the access to treat our wastewater to potentially keep it clean. And there's also other cool ways. So for instance, I just want to make mention of this. This really cool way to keep our wastewater clean is actually these solar water cones. This is really, really cool technology, really, really simple technology. You put salty water in, you use the power of the sun to get rid of the salt. Really, really cool thing. I recommend Googling it. Really, really fantastic invention by some folks to desalinate water, which again is a really hard thing to do, but a really important thing, at least going forward. So that's sort of the techniques we use to clean our water. Now, what regulations exist? There are numerous regulations, and they vary between countries, and they vary pretty heavily within a continent as well. So, China has a different water policy than, say, Russia does. So they vary pretty dramatically. But here in the United States, we have two things. The first is the Safe Drinking Water Act, and then the Clean Water Act. They're decent acts that were enacted, 30, 40, 50 years ago in that ballpark, to try to keep our drinking water safe and clean for us. Now, I think the crisis in Flint, Michigan, their issues really show that these acts don't do a great job, and they're not particularly heavily enforced. But this is what we have here in the United States. Now, who enforces these things? Well, the EPA is the one that really does it. They test our water to make sure our chemicals aren't getting in there. But as you guys know, the EPA, and as we discussed, can be oftentimes hamstrung by whatever administration's in office. So the EPA, while it's supposed to monitor these things, doesn't always do the best job because, again, due to political reasons, stuff like that. So that's why that's what we do here in the United States. We have two distinct acts. They set standards, and states are either have to meet them or exceed the standards. But again, that's not always the case, as we see with our friends in Flint, Michigan. Now, one of the other important resources for our water outside of like acts and treatment plants and stuff like that is actually glacial water. And so, as we'll discuss in climate change, globally, our Earth's glaciers have been losing significant amounts of mass, thousands and millions of square miles every year, due to climate change. That's the way it is. And again, we'll talk about climate change later in the semester. But the reality is, as we sort of saw, glaciers oftentimes feed rivers, and rivers oftentimes feed lakes and ponds, which we rely upon for drinking water. So the loss of glaciers potentially has the capacity for us to lose fresh drinking water. And again, we'll talk more about deglaciation when we talk about climate change, but I wanted to make mention of that idea here. And again, we'll talk about this idea later. And again, we'll talk about ice ages later. I don't want to talk about too much, but sort of the final sort of thing I want to make mention of is our ocean. It is the largest single habitat on the planet. 2/3 of our planet is covered at oceans at a depth of 2.3 miles, which is really, really deep, right? And so oceans are clearly important. The ocean is very, very salty, which is why we can't drink it, which is why if we tossed like a trout into the ocean, it would die because it can't handle the salt. So the oceans are very, very salty. Now, one of the things we see in oceans is actually some pretty distinct currents. And so you can see currents all over the planet. There's the Antarctic current that goes all the way around the planet along the Antarctic border. We see currents and things that we call gyres. So we see rotational forces, i.e. currents here in the Indian Ocean, the North Pacific, the South Pacific, the North and South Atlantic. So there are lots and lots of oceanic currents. And I hope this really shows you that our oceanic waters are really connected. So if something bad happens here, so say like an oil spill happens in the Gulf of Mexico, that oil makes it out of the Gulf of Mexico and makes it everywhere, right? So if you think about that, it comes out of the Gulf of Mexico, makes it all the way up, goes all the way into the Antarctic, goes all the way down to the South Pacific, Atlantic, and that once it makes there, it goes everywhere. So our oceans are really connected by these currents as well. They're massive conveyor belts. That's kind of the way you think of oceanic currents. I'm sure you guys have probably heard of like the Gulf Stream, which is this current that goes here on Weather Channel or something like that. So they play a role in our weather as well as our climate as well. So just to let you know. Now, our surface currents, so these sort of currents that are on the top 400 meters of the water, are basically occur because of air blowing across the water surface. So that's what's causing a lot of these surface currents. There are deep currents they're caused by various forces that we won't talk about. But there's also large oceanic currents that are bent, as I sort of mentioned, that are called gyres that sort of keep things moving in a circle. But there's actually a really interesting thing that causes gyres. It's actually called the Coriolis effect. Because the Earth is spherical, we get a natural bending of our winds, a natural bending of our oceanic currents. So as you guys probably know, the Earth is spherical. It's not flat, but it does spin. It does spin clockwise, so it goes right clockwise. Yeah, it does spin clockwise. Sorry, I had to think about it there for a sec. It does spin clockwise, so it rotates this way. And because it rotates, it causes the Coriolis effect where you have a bending of winds, a bending of oceanic currents. And you can really see that here, right? You see a bending of all of our currents. They're not particularly straight. So what this does, if you sort of conceptualize it, if you had a person throwing a ball, its expected path would be straight if there was no Coriolis effect. But because of the Coriolis effect, it would bend the ball again, because of the rotation of the Earth. So it again causes all these deflections of currents and things like that. And again, all due to the rotation of the Earth, and it's all bending against essentially in this way, heading towards west, creating all these nice sort of westerly pushes. Now, outside of the surface currents, there are these deep currents which interact with our surface currents. So as you can sort of see, we have these surface currents here in red, but we have these deep currents here. Now, what causes these deep currents to occur? Well, I mean, there's a number of reasons to it, but the big issue is that, not really issue, I should say. The big thing is what we call the thermohaline conveyor. So as water gets deeper, as you guys probably know, it gets colder, but it also gets a little bit saltier. And so, I'm sorry, a little less salty. So as currents move into colder regions, cold water sinks, creating these currents that go deep, but eventually they come back up, mixing with the surface currents. So we get, again, these surface currents that we sort of see here, and then we also get these deep currents as well. So our water is mixed not just around the globe, it's mixed from top to bottom, though I will say deep currents move very, very slowly. They move at a few 100 meters per year. So they're very, very slow, but again, they do allow mixing of top as well as bottom waters. Yeah, so I've already sort of said this. I'm gonna move on from this slide. And one of the effects of these types of currents is El Nino, but we're actually going to talk about El Nino later in the semester. But I want to let you guys know that these currents and how they change do affect El Nino, which we are going to talk about later in the semester. So you can feel free to take a peek at this right now, or you can wait to the climate change lecture. But again, what causes El Nino is our currents and the deep currents and stuff like that. So just wanted to make mention of it and sort of move on. Sort of the other cool thing that we can see is, well, actually, no, I'm actually going to skip this slide. We're going to talk about this in climate change. So you can read the slide if you want, but again, we'll talk about this in climate change. Now, the sort of the final part of this class is actually oceanic life. So what sorts of distinct zones does the ocean support? And you guys probably have seen or heard of many of these things. The first is what we call the intertidal zone. It's the area that basically is either covered by oceanic water at high tide or exposed during low tide. That's what we call the intertidal zone. Some pretty cool stuff lives there. You guys have probably seen there's like algae and crabs and all stuff like that. And then we have the nearctic zone, which is the area of the ocean that's basically closest to the land, where it's not too deep. It's still in what we would call that photic zone, i.e., light still penetrates. Now, in this nearctic zone, there's some pretty interesting stuff that goes on here. This is where coral reefs are, and we'll talk about coral reefs in just a second. But we also support some pretty dynamic and cool areas of the ocean of grasses and plants and stuff like that. And as you'll notice, sort of in terms of like sheer number of species, most of the ocean's diversity of life occurs in the nearctic zone. So very close to land, most oceanic diversity occurs. So, and then we have you sort of see this drop down. Now, this drop down is actually just a continental shelf. So this is the continent up here, and then we drop down into these essentially these ditches. Well, maybe not ditches, like trenches would be the better thing. And so we have the continental shelf, and then we have these trenches. And you'll notice in these trenches, we have lots and lots of large things here in the oceanics photic zone. And then we sort of drop down from what this photic zone here in the open ocean, which is called the benthic zone. We drop down into the aphotic zone, which has basically very little or no light. But as you'll notice, the ocean, unlike ponds, has some pretty vibrant life going on down here at deeper depths in the absence of the sun. So pretty cool things. So that's how our ocean is stratified. Lots of interesting habitats, lots and lots of biodiversity. The ocean holds most of Earth's biodiversity, so pretty cool thing. Now, one of the other cool things is actually in our nearctic zone, we have pretty vibrant communities. Now, humans live near the coast, and the reason we do that is because these nearctic communities are super duper productive. They produce lots of ecosystem services for us. Now, one of the best examples of this is actually coral reefs, and we'll talk about coral reefs again this semester, but but these coral reefs are super duper important. You guys have probably seen, pictures of coral reefs at some point, but awesome little animals with their little photosynthetic partners here in these corals. And these corals support huge amounts of biodiversity, huge fish biomass, sharks, and so on and so forth. And coral reefs are actually pretty important to humans as well, because not only do they support themselves, but they actually support humans. So about 2 billion people across the planet get about 80% of their calories and protein from coral reefs alone. So coral reefs supporting lots and lots of good fish and stuff like that, but also huge amounts of people, right? About 2/7 of the planet is supported by coral reefs for their primary protein source. So pretty cool stuff. But very much like our fresh water and our drinking water, we'll talk about many of these things soon. But we do affect humans. Humans do affect the ocean. Now, we'll talk about plastic and pollution later in the semester. We have a whole lecture dedicated to oceanic plastic. So that's one of the ways we pollute our oceanic water. Fossil fuel consumption, we've already talked about this one, where we talked about the Exxon Valdez spill. We also talked about the Deepwater Horizon spill, dumping petroleum products into the ocean, either on purpose or an accident. That's one of the things we do pretty well. Agricultural runoff is kind of a big deal. We'll talk about this one in the food lecture. So don't worry. We like to overfish and impact our oceanic waters. We talked about this in relation to tragedy of the commons, but we'll also talk about it next class when we talk about what this does to biodiversity as well. And then we'll talk about climate change and ocean acidification during the climate change lecture. So these are all the ways we affect our oceanic waters, as well as the organisms that live inside our oceans. Now, this leads us to the final slide of today's class, or today's first part of today's class is what can you do? The reality is most of your water usage comes from your food choices. So if you want to make any sort of difference in terms of your own personal budget, it's really all about your food choices, eating less meat, unfortunately drinking less coffee, and eating less chocolate. Eating less water intense foods is really the way to go, but also, other things including like buying better high efficiency washers, using less water when you shower, buying drought resistant plants for your gardens, and drought resistant grasses when you guys eventually buy houses and stuff like that. Those are the sorts of things you can do. But more importantly, at the the governmental level, we do need better enforcement of our policies on the book. So things like Flint, Michigan don't happen here in the United States, as well as preserving our water resources for future folks out there. So those are the sorts of things that we can do as individuals, but a lot of it again comes through policy. That's really the big thing that you can take away from this course is you can do stuff, but it's nothing if we don't enact meaningful amounts of policy changes at the local as well as at the national level. So That's going to be our first part of today's class. I'm actually going to have us take a quick break because I need to use the restroom. So I'm going to pop this recording back. And I wanted to start with this really cool thing I saw yesterday or the other day. Actually, I think I saw it yesterday on CNN. I saw it elsewhere, but this sort of thing, and it's just a quick 2-minute video, but huge and intense Oregon wildfires creating its own weather. And so it really fits with what we're going to talk about today. It really fits with climate change later in the semester. So I figured it would be a good place to start. I also love the news on the side here. It's the Surfside condo collapse and then Ice-T's baby. I thought that was funny. Such an odd dichotomy right next to one another. But let me know if the volume isn't working. It should be. I set it up so it should, but if it's not working, let me know.
This Boot Lake fire in Oregon has scorched more than 600 square miles, an area larger than Los Angeles.
Right now, this is the 4th largest fire to burn in Oregon since 1900.
It is so massive and so dangerous that fire crews have had to escape the fire 9 days in a row.
You saw multiple pyrocumulus clouds.
The fire also so intense, it's creating its own weather. The formation of pyrocumulus clouds is a phenomenon that enables the fire to create its own thunderstorms, which in turn can produce lightning, strong winds, and even fire tornadoes.
We just continue to see day after day after day of conditions that are not in our favor.
In a typical wildfire, the weather will dictate the path and intensity. But with the bootleg, experts say the fire is predicting what the weather will do. Nearly 1,100 acres burning per hour, and containment hovering just around 30%. Nearly 70 homes have been destroyed.
After last year, what is very clear is that no corner of our state is immune to fire. On the West Coast and here in Oregon, the urgent and dangerous climate crisis has exacerbated conditions on the ground.
The Boot Lake fire far from alone. More than 80 large wildfires are raging in 13 states across the country, burning more than 1 million acres. In California, the Tamarack fire has forced the evacuation of at least a half dozen communities. Most were only given a few minutes to evacuate when the fire exploded Saturday, going from 500 acres to now nearly 40,000.
We had 10 minutes to grab, what we could and the dog and got out of there.
Anxious residents allowed to return to their homes today with an escort to look around and grab some essentials.
Just hoping to see our house still standing. I know, they say it's okay, but I really want to see it for myself. It's scary.
The deputy just told us that our house is still standing. We just want to check it all out.
Sorry about that, Tim. Did anybody else have any problems seeing the video? It said it was sharing my screen. Anyways, here's the link to the video if you could not see it.
Visit litterrobot.com and join the over 400,000.
Stop playing ads. No one wants to listen to your ads. Anyways, so I dumped the video link into the chat for you guys in case you couldn't see the video or something like that. I hope you could at least hear the audio, but this really sort of massive fires, I should say, burning throughout the area of the western part of our country, but that we saw in the previous class that's suffering from some pretty severe drought year after year after year. So we see this really dramatic set of wildfires occurring in this area that is experiencing some pretty severe drought. So I wanted to sort of put that here today because it's a good foreshadow for what we're going to talk about in the climate change lecture. But I also just wanted to put there because it's sort of the part that I thought was the remarkable part is this fires, and this is not just limited to this fire or this set of fires, I should say. This is common across all large fires where they're creating their own weather systems because there's so much airflow, there's so much particulate in the air. They're creating their own tornadoes, they're creating their own clouds, they're creating their own rain systems. Really, really fantastic thing that nature is doing. Really, really, I mean, obviously very, very terrible, but at the same time, it's pretty remarkable what a single fire, I mean, it's obviously a huge fire, but a fire can do for the weather. So let's talk about weather. Let's talk about the air. Let's talk about how we mess up the air. I mean, that's the point of this class, right? Let's talk about all the bad things humans do, I guess. So we're going to start with another quote. I like this quote from Lucretius in 50 BCE. He said, air, I should explain, becomes wind when it isn't agitated. And I thought that was kind of funny, sort of both from a human perspective and it's sort of a weather perspective, right? We think about air, it's there, but you agitate it becomes wind. Then you think about it from like a human perspective, like, if I'm speaking angrily, right, that creates wind, right, and all that stuff. So I thought that was a kind of a funny quote from our friend a couple thousand years ago. So let's talk about air, but we're going to look at air first here. Yep, you had a question, Shane?
Yeah, I think you're still sharing the screen with the video on it. I don't know if you have your like notes document or presentation open.
Share screen. Let's do screen. Is that better?
Yep, that's perfect. Thank you.
Oh, that's weird because I thought I had it. Anyway, it doesn't really matter. Now that you can see, that's what matters. So we'll start with this grotesque picture of Donora, Pennsylvania. Pennsylvania, you guys probably know, not so much nowadays, though it's still certainly part of the economy there. But historically speaking, really heavily invested with the consumption in the mining of coal. For those of you that like The Office, Scranton, Pennsylvania is an anthracite coal town, right? So pretty heavy investment into coal as a fossil fuel, the consumption of coal. And when we're thinking about air, when we think about scenes like this, we get this because of what humans are doing to the air. Now, what are the major sources of air pollution? Well, in this case, we have cars, we have factories, and just the overall consumption of fuel. Now, we can sort of see this awful scene. We're going to, again, have the production of air pollution by human activity. So that's the sort of the setting for today's lecture is this sort of scene, right? This is the horrible end of it, right? But, you go into Boston, you don't ever see scenes like this, but it's because it's not progressed that far yet. If Boston had lesser air quality standards, we would look like this. So let's dive in. Let's talk about our friend, the air. So what comprises our atmosphere? Now, the atmosphere is simply all the gas from the surface of the earth or even underground, all the way up to the top of the atmosphere, just before you go into space. So that's our atmosphere. Now, our atmosphere is comprised of very, very few things. 78% nitrogen. So this nitrogen here is biologically inactive. It just hangs around there. It doesn't do anything. 20% is our beloved gas, oxygen, O2. Again, that's 20%. That's what we breathe. That's what plants produce when they're photosynthesizing. So 20% oxygen. So you can see the atmosphere is very simple. 98% is just two gases, one of which does nothing, and the other one which we rely upon so heavily for life. And then the remainder, that 1% or so, is comprised of a couple gases. Now, argon, which is you don't really need to think about, again, does nothing in the atmosphere. It's about 0.96%. Then we have water vapor. When we talked about that last part of the class, i.e. evaporated water, gaseous water, is about 1%. And then the next most abundant gas is actually carbon dioxide at 0.04%. And then there's a bunch of other small gases out there. They're called trace gases that really, they don't really matter to the sort of the way our atmosphere is, except when you're thinking about climate. So we're going to focus on the atmosphere, what it looks like, how it works, but we're going to focus on it, those trace gases later in the semester, and focus on CO2 later in the semester when we talk about climate change. So, but this is our atmosphere. It's all the air you breathe. Now, one of the things that we see with air is air pressure. Now, this is something you guys have sort of experience in your average everyday life. Now, pressure simply refers to the amount of force. Now, a force can be like I punch my hand, right? I'm applying a force of my hand punching my hand. That's a force I'm applying. Now, pressure simply looks at that force you're applying and how big of an area you're applying it to. So you guys have probably filled up the air in your bike tire or your car tire, right? You put air pressure into those. So what does pressure in terms of air mean? Well, it simply means how many air molecules I have pressing on a given surface. So high pressure simply refers to a lot of force on a small area. Low pressure refers to essentially a little bit of force spread out over a very, very large area or a larger area. So for instance, we have a balloon here. This little girl, she's blowing air into a balloon. She's doing a couple things to that balloon. She's increasing the temperature of the balloon. And we'll talk about temperature in just a moment. But she has air in her mouth. She's pushing it into the balloon, and she's adding gas molecules from the atmosphere in her lungs into this balloon. Now, what this balloon is, by putting gas molecules into the balloon, the gas molecules are always moving. That's just kind of what gas does. And the gas molecules, as they move, they collide with the balloon side, causing, as you put more and more gas, more and more collisions of that gas occurs, causing the balloon to expand. So if you ever wonder why balloons expand, it's because the gas molecules are colliding with the side of the balloon. That's what's really going on. You're applying that pressure with your mouth, but again, the balloon wouldn't expand. It wouldn't stay expanded if it wasn't from the pressure being exerted by the gas molecules. Now, the other thing she's doing is adding her warm breath, right? She's adding higher temperatures relative to the air. So what does that mean? Well, for those of you guys who have ever blown up a balloon before, you blow it up, say it's the size of like a baseball or something like that, and that's at room temperature. And then if you took that balloon and you put it in the freezer and you came back in an hour, you would notice that that balloon is much, much smaller. So what's going on? Well, temperature, as we'll sort of define, is really, and we'll get to temperature in a sec, but just to sort of tell you in the context, is that we have temperatures defined by how fast molecules are moving. So if molecules, when they're warm, i.e. have a high temperature, are moving very fast, it also increases the pressure. But if we think about our balloon example, if we decrease the temperature, the molecules are moving much less fast, the air molecules, of course, leading to less pressure, leading to the balloon collapsing, coming down, becoming smaller. So temperature and pressure are related. There's some pretty cool physics behind it. If you want to look it up, it's called the ideal gas law. But that's just sort of how pressure is related to temperature. It's kind of an important thing. So let's look at pressure relative to the atmosphere. Now, atmosphere exerts a pressure on you. Now, how does it exert a pressure? Simply because no matter where you are on the planet, there is a column of air above you. It's kind of a weird thing to think about, but you can sort of see this picture here where we have elevation in kilometers all the way up to 50 kilometers, which is about the top of the atmosphere. And we have, all this stuff here, which is fine, where we have pressure. What you'll notice is that the pressure is very, very low at the top of the atmosphere. And you'll notice here on the white part, we have 3 gas molecules, which means there's very, very little air at the top of the atmosphere. The gas molecules, of course. Then as we come down in elevation, you'll notice the pressure increases. That's what this red line is referring to, until we get down to the crust of the earth, right? The surface of the earth, where pressure is very, very high. Now, why is that pressure high? Well, there's much more air molecules here, right? And there's more air molecules stacked above you. So when we think about air pressure, it's really just how much air do you have stacked on top of you. When you're at the surface of the earth, there's a lot of air stacked on top of you. When you're at, say, the height of a plane, there's significantly less air stacked upon you. So when if you guys are like me, or if any of you are like me, and you hop on an airplane and you get up to 30,000 feet or so, and your ears immediately pop, right? Well, what's causing your ears to pop? Well, there's less air pressure up there. So the pressure, which is really important to how the way your ears function, that change causes your ears to essentially pop because, again, there's a change in pressure leading to your ears changing in their structure, creating that little pop sound that your ears get. So if you ever wonder why your ears pop in an airplane, or why they would really pop if you did a really high skydive, like this gentleman, Alan Ustash, that's why, because there's less pressure leading to your change in your ears, leading to the popping of your ears. So that's our atmosphere. Pressure is related to how much gas molecules there is. The higher you go, the less gas molecules, the less pressure. Now, the other thing I'll say, when you think about a plane cabins are pressurized. Why? Because there's less pressure up high than there is on the surface. So how is the Earth's atmosphere constructed? What does it look like? Well, again, it's not very big. If you could hop in a car and drive vertically at 60 miles an hour, you'd escape the Earth's atmosphere in about 1 hour. So it's only about 60 miles or so high, very, very small. But this atmosphere is incredibly important for life. It's incredibly important for our climate, for our weather, and so on and so forth. Now, the top of our atmosphere is the thermosphere. This is where the International Space Station, as well as our satellites, hang out. It's about 90 kilometers. Then we have the mesosphere, which is the next layer. Not a lot of cool stuff happens here, just as a note, just the mesosphere kind of hangs around there. It gets very, very cold though. Sometimes the temperatures, as the slide says, can get well below freezing. 148 below 0 Fahrenheit is no joke cold. Then we have the stratosphere. The stratosphere is pretty cool. The stratosphere does a lot of stuff at about 30 miles above Earth's surface. But one of the things that the stratosphere does have, and we'll talk about in just a moment, is the ozone layer. And we'll talk about that in just a moment. But the ozone layer is a really important part of the stratosphere. And then we have the polar stratospheric clouds. Those are the highest clouds you see out there. They're not very common, but they exist. And then you finally get to the troposphere, and this is basically where we exist. Everything basically we do, even if you hike to the top of Mount Everest or hopped on a jet, commercial jet, of course, not like a spy plane or Air Force One or something like that, you basically never leave the troposphere. I mean, I'm sure you guys probably saw like Jeff Bezos and Richard Branson were up in the thermosphere recently, but most people will never leave the troposphere because that's where pretty much everything exists. Our clouds, our weather, and remember, it's closest to the planet. That's where most of our gaseous molecules are. So that is our atmosphere divided into distinct sections. We mostly focus on the troposphere because, again, we live here. We pretty much never leave here. A very select group of people have left the troposphere in their lifetimes, astronauts and billionaires and stuff like that. So not very many people leave the troposphere. So this leads us to talking about weather, because as I mentioned, all weather happens in this lower part of the troposphere, but weather is important for lots and lots of different things, right? In the previous section of today's class, we talked about water. Weather, i.e. rain and sleet and snow, really important for the way our aquifers, really important for our water or droughts, things like that. So we're going to talk about weather because, again, it is directly influenced by our atmosphere. Now, weather is short-term variations in temperature, moisture, wind, humidity, and all the things you can see on the Weather Channel or in an infographic like this on a very short period of time in a given region. So today, it's nice and sunny, it's a little humid, and it's about 75 degrees here in Massachusetts. That's the weather in Massachusetts. However, that's different from climate. And we'll talk about that more later in the semester, but just to preface it today, climate is long-term patterns. So if I told you that for the past decade, the average temperature in July was 85 degrees, that refers to the climate, long-term changes, long-term trajectories in weather. So weather is short-term. What is the weather like today? Climate, what happened over a decade-long period? I really like this quote from Mark Twain because I think it does a pretty good job of illustrating the difference between climate and weather. And one of the greatest authors of all time says, "Climate is what you expect, weather is what you get." And I think that's pretty great. Every place is like this, but I'm sure you guys that live in New England or grew up in New England know that New England weather can change rapidly and does crazy stuff like giving us snowstorms in April and stuff like that. So weather is what you get. Climate is what you expect. Love that quote from Mark Twain. So as we've discussed, there are different ecosystems on planet Earth, and those ecosystems have different abiotic conditions. So how do those abiotic conditions arise? Now, one of the biggest things that affects the abiotic conditions in an ecosystem is simply temperature. And temperature simply measures two things. Mostly just measures two things, hotness and coldness. If the temperature is high, it's hot. Temperature is cold, it's cold, right? That's something you guys know, right? If it's hot, you put a t-shirt on. If it's cold out, you put a jacket on, right? And how do you measure temperature? Well, you measure it with a thermometer. I don't really need to tell you guys that. You know that. Stop biting me. Now, I could ask you the question, how is the Earth warmed? And the answer is simply our beloved sun, right? Just a one-word answer. What heats the Earth primarily is the sun's rays. Now, there's some other stuff that influence how warm the planet gets. Stop it. Sorry, my dog's biting me. That influence how warm the planet gets, but we'll talk about that during climate change because it's much more relevant to that. But again, what influences how warm the planet gets is the sun. Now, the sun produces a crap ton of energy because it's doing all sorts of cool processes inside, but it takes about 8 minutes for that radiation or that light from the sun to get to the Earth. It travels 93 million miles at the speed of light. Now, as you guys probably know, Different parts of the Earth have different temperatures. And so you guys probably know, and we sort of discussed this, the tropics have much warmer temperatures than, say, here in New England. Now, why is that? Well, the reality is you can actually do a really simple experiment in your own house to figure this out. This is actually one of the ways you could, if you ever wanted to convince someone that the Earth is round, that you could do this experiment as well. But if you take a flashlight and you shine it at your light at your wall, if you do it at a straight on angle at 90 degrees, you'll notice that the light catonates at a single intense beam. If you ever used a flashlight, you know that's sort of what it does. Now, if you take that same flashlight and angled it, as you see here, at about 50 degrees, you'll see the light essentially spreads out. So the light becomes less intense overall. And so we can apply this idea to our planet. Now, if we think about the sun, it's over here somewhere. We orbit around the sun. Because the Earth is spherical, because the sunlight comes in at the equator and it's hitting at about a 90-degree angle, it's pretty intense, right? It's intense, consistent sunlight at the equator, which makes the equator much, much hotter than the rest of the planet. Then we also have sort of the angle of the Earth. So as we go up and up and up, and you can think about it as we like sort of change the angle of our flashlight, the intensity of the sun goes down and down and down. The more north and the more south you go. So we get these sort of, the equator is really hot because it's direct, intense sunlight. And then we get these colder areas below the equator because of the slanting of the sunlight, making the sunlight overall less intense. And the only way that actually works is if the Earth is spherical. It's just the only way it works. If the Earth wasn't spherical, this simply wouldn't work at all. Just as a note. So if you ever run into anyone that doesn't believe the Earth is round, it's a simple and easy way to show them how the Earth is round. It's just simply because of our climate. Now, as we talked about when we talked about the water cycle, we know that water is in the land, it's in the ocean, it's in lakes, ponds, but it does evaporate. And as it evaporates, it becomes water vapor, comes up into the atmosphere, creating clouds. And that creates clouds. It also leads to humidity. And when you have cloud cover, it does a couple things. It creates precipitation, but it does some other things that we'll talk about in the climate change lecture in terms of regulating climate. Now, one aspect of the amount of water vapor that we see in the atmosphere is humidity. And so you guys, being people that go to school in the Boston area, you know Boston can get quite humid. Now, what actually is humidity? It's just simply how much water is in a given volume of air. So higher humidity simply means there's more water vapor in the air. That's simply it. It's kind of a nice thing. Now, one of the things that this affects is actually one of the things that actually affects is evaporation. So when humidity is very, very high, one of the things we actually see is that evaporation actually slows. And you might ask yourself, why is that? Well, if there's a lot of humidity in the air, there's very little places for that water to go in terms of evaporating. So lots of humidity prevents evaporation of water, just as a note. Now, we can put this in context to our friend here, Roger Federer, arguably one of the greatest tennis champions of all time. But we have Roger Federer over here, and he has this really nice quote after his 2018 bout at the US Open. He says, "Just one of those nights where I guess I just couldn't get air. There was no circulation at all. Yeah, it's uncomfortable. Clearly, just kept on sweating more and more and more and more as the match goes on, and you lose energy as it goes by." Now, what is Roger Federer really getting at here? Well, the US Open is played in traditionally places that have very high humidity. So Roger Federer just kept sweating and sweating and sweating, trying to cool himself, but the humidity was so high, he just couldn't cool himself down through increased sweating. So he was sweating, but again, he was still feeling very hot, very sticky, because again, the humidity was preventing his body from naturally cooling itself. So if you ever wonder why working outside or going to going on a hike when it's very humid makes you feel hotter overall, it's because you can't naturally cool yourself, because increased humidity prevents evaporation of water and prevents sweating from working. So fun things. One of the other things we see with our atmosphere is barometric pressure. You guys have probably seen a map like this at some point in time. If you've ever watched like the Weather Channel or looked at a map of weather, you've seen these lines before. But I would wager guess no one ever probably bothered to look at what they mean. So we'll talk about what they mean, just because I think it'll you guys will find it interesting, but this line refers to pressure systems. Now, we have this idea of barometric pressure, which simply is a measure of the pressure exerted by Earth's atmosphere at any given point. Now, what changes Earth's pressure? Now, I'm going to go back a few slides where we have this figure here. Now, pressure is highest at the bottom, right, on the surface, but the column of air here in the atmosphere is pretty consistent around the globe. So how do we get different areas of pressure, given that the column of air mass everywhere on the planet is exactly the same? Well, the reality is we get changes in pressure by actually changes in two things. The first is temperature, as well as just movement of air, i.e. air currents. So we get changes in pressure along the planet due to our changes in temperature, as well as the changes in air. So let's look at how this happens. Now we get a low pressure system where as air warms, it rises. I'm sure you guys have probably heard that warm air always rises. That's just what it does. So warm air, as the air on the bottom warms, it rises up. And what this does is it causes basically essentially like a vacuum to pull air in on the side, again, creating an upward draft, but also sucking things in the side, creating an overall low pressure system. Now, the other thing this does, it also causes air to spiral upwards and counterclockwise at very, very low levels. So that's what we have, a low pressure system. And then we have a high pressure system, which is exact opposite of it, where things start to cool down, causing air to sink, creating essentially a vacuum, pulling things down, causing air to essentially spiral clockwise out at low pressure, but also causing a net pull up around that downward pull. So again, this is how we create our low pressure and high pressure systems, hot and cold. Now we can look at this in terms of fronts. So we have this hypothetical map here of the United States and Canada and Mexico, obviously. Where we have, again, these H's here, which refer to high pressure areas, and there's L's here, which also refer to low pressure areas. And then we have what we call cold fronts and then warm fronts. So we have cold fronts here in blue, and then we have hot fronts, warm fronts, I should say, here in red. But you'll notice that the front, while it's moving, it sort of spans a pretty large region. It can be both cold and warm at the same time. But you'll notice areas where there's low pressure, typically speaking, we see areas that are very like cold because they're sort of dragging the warm air up, creating slightly colder areas. And then sort of vice versa, you see typically, well, I don't have any examples on this map, but you kind of get the idea. So again, we have this overall pressure here, changes due to temperature and changes in air currents, creating high pressure and low pressure, or just simply changes in barometric pressure. And you can sort of see this with our friends over in California, where we have these high pressure systems, and they're pretty common. And so in this nice map is actually from 2011 to 2016, where there was a high pressure system off the coast of California here in the Western United States. And this was actually this really consistent high pressure. And so they had this really high pressure event, which was actually essentially diverting storms away from this area around and down across the United States, creating some pretty intense systems. Now, you might think what does it really matter? Well, if you think about what was happening in California in this time from 2011 to 2016, there's some pretty severe wildfires, pretty severe droughts. So one of the causes we commonly see in California for causing some pretty severe droughts is oftentimes buildup of high pressure systems, diverting storms away, creating an overall drier area. And as we sort of looked at the video at the start of this class, again, we had a very, very high pressure, very, very dry area, very, very fire intense area here, again, because of the buildup of high pressure systems. So these pressure systems don't just affect our weather, they also overall can affect, sort of natural disasters such as fires. So the other part of pressure is wind. Now, wind, you guys know, is just the movement of air, right? It can either be like I turn a fan on and it pushes wind across the room, thus I feel cooler, or it's, I stick my hand out the window of a car and I feel the wind bashing into my hand, pushing against my hand, or it's just a natural breeze coming down. Now, wind is again simply the movement of air. Now, wind itself, as you guys probably know, helps create storms, and we sort of saw that here, right? Where we're seeing a movement of air, i.e., wind, helping create high as well as low pressure systems. Now, we can also see and so we sort of already talked about the idea of cold air replacing warm air, our cold fronts, and warm air replacing cold air with our warm fronts. Sorry, cold fronts and warm fronts. I mixed those up. But the other thing that happens is these these wind or these fronts actually create essentially high pressure systems or low pressure systems. And if they're strong enough, it actually causes essentially to basically like act like magnets to essentially suck in air from other places. So if we think about something like a hurricane, hurricanes, you get these very, very low pressure systems. And because the pressure gets so low in these systems, in these areas, it pulls and pulls airs in, eventually creating these convection and spinning currents. And as the pressure drops and drops and drops, it continues to pull more and more and more air in, spinning faster and faster and faster, eventually to create these very large hurricane events. So again, low pressure events lead to some pretty severe storms, some pretty severe winds. High pressure events typically, or I should say high pressure fronts or yeah, events is fine, typically create better weather, just as a note. Now, the other thing that affects our air and the way it flows is actually land masses. So I'm sure you guys probably know hurricanes do really great over the ocean, but once they hit the land, they pretty much dissipate within a few days. Why is that? Well, large pieces of land essentially don't have the same, they have like a topology to them, unlike the ocean, which is just flat. And so this changes in topology, weakens air currents, changes pressure, allowing hurricanes to sort of dissipate, winds to dissipate as they go over land, generally speaking. The other way you can sort of see this is actually during in the Midwest. Midwest, as you guys probably know, is very, very flat, but the Midwest still has lots of winds. Now, the winds in the Midwest whip up because of changes in air pressure, as we discussed, but there's actually no large land masses to divert the winds in the Midwest. So they oftentimes can get really, really high winds in the Midwest because, again, the topology of the terrain. Unlike here in Massachusetts, where we don't get super high winds most of the time, unless they're coming from the ocean, simply because we have so much terrain in Massachusetts. Now, the other thing we commonly see is actually what we call the lake effect. I think it's a pretty cool thing that you can see. So if you know anyone that lives, say, in Buffalo, or they live on one of the Great Lakes, either in the United States and Canada, they get what's called lake effects. Now, large bodies of water, including the Great Lakes, can actually produce a really interesting effect, again, called the lake effect, where basically they intensify snow and rain production, leading to higher levels of precipitation. So, for instance, my sister, she used to live up in Rochester, New York, right by Lake Ontario. I forget if it's Ontario or Erie, one of the two. Pretty sure it's Ontario, though. And she used to get some pretty severe snowstorms up in Lake Ontario, because up in where she lived, because of the lake effect. So the lake effect brings some pretty awesome precipitation events with it. Now, we've sort of talked about wind, but there's very much like when we talked about the water, there's pretty consistent air patterns all across our atmosphere, as there is pretty consistent currents throughout our global oceans. And so let's talk about those. So let's talk about how changes in atmospheric pressure lead to what we call prevailing winds. So let's just take a peek at it first. I think it's easier to understand. Let me just go ahead to one. So we can see this nice little figure here where we see our prevailing wind patterns, where you see pretty consistent wind patterns occurring here. We see the Coriolis effect, creating wind currents that push this way on both the north and the south. North and south of the equator. We see a polar front, i.e. the jet stream. You guys have probably heard that one before. But we also see these currents that happen all along, well, the currents isn't the right thing, air fronts that happen all the way along, all these wind fronts that occur. So now, one of the cool things we actually see on our planet is actually the production of these really cool things called feral cells. And they're also called Hadley cells when they're along the equator. So Ferrel cell, polar cell, Hadley cells. Now, this is actually a pretty cool thing that occurs. Now, it only happens for Ferrel and Hadley cells in areas that actually get warm. You have a polar cell, which is just a circulating current of air over the North and South Pole, just as a note. But these Ferrel and Hadley cells are pretty cool. Now, as you guys probably know, the equator is pretty warm. So lots of sunlight causes lots and lots of warmth to occur, lots of evaporation to occur. Now, because of lots of evaporation of water, we create lots of storm systems, lots of warm air and warm water coming up to the atmosphere. Now, what ends up happening is because of sort of the air currents that occur in this region as well as this region, we actually have a really fascinating thing where the warm air evaporates, gets pulled over the atmosphere and dumped down into these areas that are essentially subtropical, as we see here and as we see here. So they're warm, but not super warm. And then as the air goes up to the atmosphere, it cools. Then it falls, it starts to warm up again, and essentially repeats this thing over and over again, creating us a Hadley cell. Now we see the same thing here in the northern hemisphere, as well as in the southern hemisphere, called Ferrel cells, where we have cold air comes from the north, falls in these subtropical areas, warms, rises back up in this current, and rinses and repeats this entire thing. So we have these Ferrel cells, we have these Hadley cells. Now, one of the cool things this does is it actually creates some distinct ecosystems. Now, you'll notice that there's no overlap between Ferrel cells and Hadley cells. There's this like gap. Now, you can actually see this in this figure here, which is actually pretty cool, where you have these warm tropical areas here and here, and they're getting all this nice rain. But you'll notice that the current goes over, and again, it gives these blank areas here, 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 and here. And as you sort of pick up from this figure, these blank areas actually happen to be where deserts are. So all the great deserts in the world occur at 30 and 60 degrees north, as well as 30 and 60 degrees south. So you guys probably know the American Southwest, the Chihuahuan Desert, the Mojave Desert, all right here. The Gobi Deserts in China, about here. This area of the globe, again, also pretty dry. Antarctica is just one giant big desert, just as a note. The Atacama Desert is here. So all the great deserts of the world form at 30, 60 north and south because of these Hadley cells and Ferrel cells simply not overlapping at all with one another. And again, why is it? Again, our air currents are generated by changes in temperature, changes in the movement of water, leading to this pattern that we see. So pretty cool thing. If you ever wonder why deserts are all concentrated in one area, or if you ever wonder why the tropical rainforest is so wet, again, it's because of these little cells that form. I think a pretty cool thing. Now, as we mentioned, our winds are affected by changes in pressure, and they're also affected by that Coriolis force, as we discussed. That's why we see a bending of winds as we approach the equator. Remember, that's what the Coriolis force does. Now, we also see a pretty interesting set of things, which we call jet streams, which are a set of prevailing winds that form about 6 miles above the Earth's surface, near the top of the troposphere. But they act as like an overall sort of like master current atop of our sort of lower lying currents that help direct things, help direct weather and things like that. So very much like our oceanic currents, there is lots and lots of movement of our air. And it really does highlight that what we do here in, say, the Midwest affects what happens in New England, right? Because we're all connected by the same set of air currents, both locally as well as globally. Now, one of the other things we can see, and just to sort of highlight how connective atmospheric circulation is we can actually look at atmospheric dust transport. Now, as you may or may not have noticed, there's a polar stream that comes like this. So it comes from like Arizona and Southern California all the way through the Midwest. Now, one of the things that we see is actually we have the Mojave Desert. And because there's this air current that comes through, the air will actually pick up dust and transported elsewhere. So we see a picking up of dust here in the Mojave Desert. Now, inherently, desert soil is really, really good. It's just very, very dry. So there's lots of nutrients in desert soil. So when desert soil gets picked up by an air current and carried somewhere else, so in this case, we're going from the Mojave all the way over to the Colorado Plateau, It brings all this dirt and dust from the desert, again, that has lots of nutrients in it, over to the Colorado Plateau, and basically seeds the Colorado Plateau with lots of good nutrients. So we see the Mojave Desert looks pretty dead and sad, but then we see the Colorado Plateau, very, very lush and unique and just an overall awesome looking ecosystem. And part of that reason is because air is carrying dust. Now, this happens in the United States, but we also know there's a nice little air current that comes all the way across from Australia, from Africa. Now, one of the things that we actually see in the Caribbean is that African dusts from the Sahara Desert are carried across these wind currents and deposited on the Caribbean area, essentially giving the Caribbean area some nice nutrients from the nutrient-rich deserts in Africa. So the atmospheres don't just bring air with them. They don't just bring water vapor. They bring dust, but they also bring pollution with them. Now, pollution takes a wide variety of things. It's either human induced, like it's, exhaust from cars, or it's things that are naturally produced, like volcanic ash, pollen. Pollen is considered a pollutant. Salt from the sea. So as waves are get larger and larger, they expel salt up into the atmosphere, and it can be transferred via our wind currents, as well as soot from fires, as well as from our own things. So all these things are, while they're natural, are technically considered air pollutants. So when something is burned, when something is essentially agitated, it brings things up into the atmosphere, and the atmosphere can uniformly distribute them out across the planet. So kind of a cool thing that we see as the atmosphere. It's cool because of how it works, but it's also not great because if you're like me and you're allergic to pollen, the job of the atmosphere to pull pollen around the planet kind of stinks. So just as a note. So let's dive into some of the pollutants that we see. The first is what we call our primary pollutants. These are substances that are directly emitted from something and are harmful, and there are a wide variety of things that we can see. So a common pollutant that we are exposed to on an average everyday basis is actually carbon monoxide. Carbon monoxide is produced when we have what's called incomplete combustion, when a car is idling or your furnace isn't working great down in your basement. But carbon monoxide, or CO, is a primary pollutant. Other primary pollutants include stuff applied to agricultural areas like fertilizers, also benzene, which is produced via gasoline production, as well as asbestos from construction. These are all primary pollutants. And a specific aspect of primary pollutant is actually what we call particulate matter, which is basically anything less than 10 microns or 10 micrometers in size that can basically be suspended in the air. This is a wide variety of things, including dust, pollen, mold, bacteria. Human hair is technically also considered, and dog hair is technically also considered a primary pollutant. But there's lots of things that sort of make up our primary pollutants. But not all our primary pollutants are less harmful, right? I mean, hair and pollen and dust, they're not particularly harmful, but there are some pretty severe pollutants that are primary pollutants, including heavy metals, lead, mercury, arsenic, which can easily be aerosolized and travel in the air. We'll talk about actually mercury poisoning later in the semester, but just know that mercury poisoning is a primary pollutant. So keep that in mind when we talk about mercury poisoning later in the semester. And there's lots and lots of other stuff out there. Now, one of the things that we can actually commonly see is lead. Now, lead used to be very, very common as a primary pollutant because there is commonly a decent amount of lead in our petroleum products, as well as we used to have lots of lead in our paint. Why do we have lead in our paint? Well, lead is really good at killing bacteria. So lead paint was great for keeping places bacteria and fungi free. But we did used to have a lot of lead in our paints and our gasoline. But in the 1978 and 1986, we actually passed 2 laws preventing lead from being put in our paint and from being put in our gasoline. So when you guys ever fill up your car at the gas station, it says unleaded gas. That's because in 1986, we passed a law preventing lead from being found in gas. Now, why do we care about that? Well, lead is a toxic metal. And once it's aerosolized, it actually causes some pretty severe neurological issues and developmental issues for children. So it's a particularly damaging thing. So again, 2 pretty successful acts by removing lead from paint and removing lead from gasoline. Now, this moves us to our secondary pollutants. Now, secondary pollutants basically are, there's a couple ways they arise, but they commonly arise from just primary pollutants. So when we have some sort of this hypothetical area here where we have, the ground is cooler and then there's some pollutant here. This pollutant rises into the atmosphere, it gets trapped by what's called an inversion layer. We're not going to talk about what that is, but just know pollutants oftentimes get trapped in the atmosphere. And as pollutants get trapped in the atmosphere, they can actually start to react with other chemicals to change, becoming potentially more toxic, or sometimes less toxic, or sometimes equally as toxic. Now, an example of this is actually smog. And you guys probably have heard smog before, but smog is just a mix, sort of combining of smoke, i.e. the SM part, and fog, the OG part, into smog, which is essentially the combining of particulate air pollution with fog, creating smog. So kind of a fun thing. Now, smog actually is actually a mixture of secondary pollutants. Now, remember, secondary pollutants are things that come to be in the atmosphere. So, for instance, one of the most common things we actually see as an atmospheric pollution is nitrogen oxides. Now, as we combust our fossil fuels in our cars and factories and stuff like that, we produce nitrogen gas, which reacts with our gases in the atmosphere to produce a secondary pollutant called nitrogen oxides. So, and again, nitrogen oxides are one example. Then we have smog. That's another example, again, of secondary pollutants in our air. Now, this leads us to an important part of our atmosphere, and actually a part of our atmosphere that can be toxic to humans, but is also super duper important to humans, and that is our ozone layer. Now, ozone, if there's too much of it in our troposphere, remember the troposphere is where we live, it can actually cause some respiratory problems for humans. So that's a problem. But ozone typically only exists up in the stratosphere. So remember, that's the next layer up in our atmosphere. Now, you might ask, why are we spending time talking about a specific part of our atmosphere? Well, it's actually a really, really important part of our atmosphere. Now, ozone, O3, is actually produced when ultraviolet light from our atmosphere, I'm jumping the gun here. When oxygen in our atmosphere reacts, so we have free oxygen here, reacts with O2, which is the oxygen we breathe, producing ozone, or O3. Now, ozone in the atmosphere is really, really cool, because what it does is it actually will absorb ultraviolet light, fracturing, producing O2 again and a single oxygen, but at the same time, it absorbs the ultraviolet light. So it breaks apart, but it got rid of ultraviolet light. So what the ozone layer does in our stratosphere is actually prevents most of the ultraviolet light, about 99% of it, from actually reaching the surface of the Earth. Now, you might ask yourself, what happens when ozone breaks apart after it absorbs UV light? Well, it actually just reforms back into ozone relatively rapidly. So it's kind of a cool thing. The ozone layer is self-regenerating if it absorbs ultraviolet light. Now, you might ask yourself, why do I care about ultraviolet light? Well, if you're like me, you know the struggles of ultraviolet light. I'm sure you guys have probably seen, I have very, very fair skin. If you're like me and you have very fair skin, you worry about sunburns all the time. You worry about skin cancer when you go outside. So you apply all sorts of suntan lotions, a sunblock to prevent sunburn and stuff like that. So what's happening when you get a sunburn, and this is going to sound really terrible, but what ends up happening is the UV light comes in, it damages your skin. And because it damages your skin, what your cells do in response to that is they actually kill themselves. I know that sounds awful, but that's what they're doing. They kill themselves. And when you start to see a sunburn form, it's just a bunch of your dead cells. So if you ever get a sunburn, you see it's all red, it's just a bunch of your cells that basically killed themselves. That's why it's all nice and red. I know that sounds awful, but that's what's happening. And so if we think about what else UV light does, UV light also damages your DNA. And so your DNA, if it gets damaged, can lead to cancer. So even if you have dark skin, when you go outside, you should always apply sunblock, because again, to protect against UV. But again, the ozone layer prevents 99% of the ultraviolet light from making it down to the planet. So what the ozone layer does is it really makes life on Earth possible. Without the ozone layer, there would be simply too much ultraviolet light making it down to the surface. Thus, the ozone layer, while small, is very, very important for life. Now, like most things that are valuable for life, of course, the humans have destroyed the ozone layer in some way, shape, or form. Now, in 1970s, Lovelock, Rowland, and Molina, so 3 really awesome scientists, actually discovered that a category of refrigerants, so our former refrigerators used to be used to get cooled by a class of chemicals called CFCs, or chlorofluorocarbons. And so what ended up happening is these CFCs would react with ozone, getting rid of the ozone from the atmosphere. So you can imagine if refrigeration has spread wide enough along the planet, which it had by the 70s, and there's lots of these CFCs hanging around, our ozone layer is going to suffer, and you'd be absolutely right about that. So you can see here, we have the Antarctic Peninsula here. The Antarctic island here, and the peninsula is right here, and South America's here. But you notice that these red areas are areas where there's very, very high amounts of ozone depletion, and then the blue areas where there's lesser ozone depletion, and then you have green, which is just normal ozone. But you'll see in 1979, there was lots and lots of red, lots and lots of blue, implying that the ozone layer is being depleted. Now, you see that from 79 to 87, and then up to 2006, the ozone layer recovers pretty well. Right? There's not a lot of red here. Now you might ask yourself, why is that the case? Well, in 1987, we actually enacted what was called the Montreal Protocol, which promised to phase out the production and use of CFCs within 5 years, so before 1992. And so you can see the effects of the Montreal Protocol pretty dramatically between 79 and 2006. But then you go, well, what the hell's going on in 2018? I'll spoil the answer. This is actually because of a gas called nitrous oxide. Nitrous oxide, which is produced when we combust fossil fuels, actually depletes the ozone layer as well. So we'll talk more about this in the climate change lecture, because nitrous oxide is a very potent greenhouse gas. But just know we did a really good thing in 1987 with the Montreal Protocol, and then reverted it completely right back with increased access to fossil fuels. So just as a note, our problems with the ozone layer simply are not going away, at least not for the foreseeable future, as we combust fossil fuels on this planet in the sheer amount that we currently are. So, all right, so let's move on to another interesting aspect of pollution and our atmosphere, which is actually acid rain. Now, acid rain used to be much more common when coal was really an abundant source of energy for the planet. But acid rain still exists quite a bit across the planet, especially in poorer areas of the world. In particular, China, which has a lot of coal-fired power plants, experiences acid rain pretty regularly. Now, what is acid rain? Well, normal rainwater is, as I've mentioned previously, slightly acidic. It has a pH of 5.6. Now, just in case you've never heard of pH before, pH simply refers to how acidic something is. So a pH of 7 is completely neutral. It's not acidic at all. A pH less than 7 means it's acidic, and pH goes all the way down to 0. So pH of 0 is very acidic, where a pH of, say, 5.6 is acidic, but not very acidic. Now, if you go over a pH of 7, you start to become what's called basic. It's also called alkaline. And in the alkaline, the pH scale goes all the way up to 14. So a pH of 14 is very basic, or very alkaline. But again, every liquid on the planet falls on the pH scale somewhere. You can either be acidic with a pH less than 7, neutral with a pH of 7, or basic with a pH greater than 7. So that's our pH scale in a nutshell. And just to put this in perspective, like common things you use, like, so for instance, pure water has a pH of 7, a can of soda has a pH of about 3, your dish soap has a pH of about 12. So common household items fall somewhere on this pH scale. Now, as we started combusting more and more fossil fuels, we actually saw a rise of 2 distinct types of gases. The first is actually sulfur dioxide, SO2, and nitrogen oxides, NOx. And X can be 2 or 3, just a number, just refers to how many oxygens there are. So these 2 gases are pretty cool gases. Now, nitrogen oxides we'll talk about quite a bit, and we'll also talk about sulfur dioxides a little bit during climate change. But when these gases get to the atmosphere, they actually do something interesting. They react with all the water in the atmosphere. Remember, our atmosphere is about 1% water. And they actually form two acids. The first one is sulfuric acid, which is a very strong acid. And they form another acid called nitric acid, which is kind of a middle of the pack acid. Now, as these acids are formed, and as with all rain on this planet and all liquids in the atmosphere, they eventually fall down to the planet. So you can imagine if I produce a bunch of acids in the atmosphere, they'll hang around in the atmosphere for a little bit and eventually fall as the form of rain, which is what we typically call acid rain, or simply called acid deposition. Now you might ask yourself, why is that a big deal? Well, if you, as a sort of a one-off event, it's not a big deal. Just one bout of acid rain, it's no big deal. But with enough acid rain, you do a couple different things. The first thing, you'll start to kill trees and you'll start to kill plants. Why is that? Well, decreasing the acidity of the soil is a bad thing, right? That just makes it harder for plants to grow. And as you can sort of see from this diagram, the plants on this mountain are starting to die up because of the acid rain. Now, the second thing, eventually rain will make it to the water. Now, if it makes it to the ocean, it's no big deal. The ocean doesn't really care because the ocean is just so massive. The ocean doesn't really care. But if enough acidic rain makes it to our rivers and our lakes and our streams and our ponds, it eventually leads to the acidification of water. And once water starts to get acidified, it actually is really hard for a lake or a stream to bounce back. And so usually these are permanently acidified, leading to the death of plants and death of insects and the death of our friends, the fish, leading to the disruption of our ecosystems, as well as all the ecosystem services they provide. Now, we've seen this pretty heavily, the effects of acid rain on the Canadian as well as New England and New York forests and lakes and streams. So we've seen that pretty heavily. Now, we also have seen some pretty dramatic effects of acid deposition and acid rain on our statues. So for instance, here we have this cool little statue in Lichfield Cathedral in England of this guy with his sweet hairdo and his sweet crown. But you can see there's all sorts of damage to this statue. And this is not damage because people are hitting it with a hammer or anything like that. It's actually just because of the acid rain. The rain is really acidic. It's reacting with the minerals inside the statue, causing the statue to start to weather down, to break apart, to start to fall apart. And so acid rain is not just bad for our natural environments, it can also destroy some really awesome, well, I wouldn't call this a really awesome statue, but there's also other statues out there that are really awesome that have been ruined, at least partially, by rainfall. Now, the reality is not all places on the planet actually experience acid rain equally. So for instance, here in New England, our soils are very, very rocky, and we have lots of granite, which actually doesn't do too well in the presence of acid rain. So in New England, we actually get hit pretty hard by acid rain. We don't have a lot of buffering capacity against acid rain as a whole. However, our friends in the Midwest, including Michigan and Wisconsin and Minnesota, they have pretty heavy, pretty cool soils because their soils are chock full of calcite from a rock called limestone, which helps neutralize any acid rain they see. Now, we can actually physically see this. Now, for those of you that know anything about Michigan, as you're going up to the upper peninsula, there's a really awesome bridge called the Mackinac Bridge, and the Mackinac Bridge crosses the lakes out there, or the lake out there, and there's a cool little island off of that part of Michigan called Mackinac Island. It's a pretty cool place. There's they don't allow cars there at all, so you actually have to walk and bike places. But it's a really sort of nice area if you're ever in the Michigan area. But one of the cool things that actually exists on Mackinac Island is actually the arch. It's called arch rock, and it's made out of limestone. Now, as I mentioned, there's lots and lots of limestone in the soils of Michigan and the Midwest, which makes them less susceptible to acid rain. However, Mackinac Island has a pretty large piece of rock of just limestone. And as you can see here, this limestone has basically been cut out. Now, what's it been cut out by? Well, part of the reason this limestone has been cut out and into this really cool arch shape is by acid rain. Now, acid rain, again, cuts through this limestone, eats away at it, creating this cool arch effect. And the final thing I want to make mention of before I I sort of move on to talk about other pollutants in the air is actually that acid rain is natural. You might ask, how is acid rain natural? Well, sulfur dioxide is produced by volcanoes. So acid rain can be naturally produced by volcanoes. And nitrogen oxides are also naturally produced by microorganisms. So acid rain is natural, but the sort of the frequency of acid rain we're seeing and the intensity of acid rain we're seeing is mostly because of fossil fuel combustion. So just as a note, acid rain is natural. It can help produce some cool things like this. But again, the frequency and the intensity that it's occurring only really occurs because of humans. All right, so let's talk about some of the laws that have been enacted to respond to air pollution, because the figure I showed you to start this was a picture of Pennsylvania, and the air looked really awful and gross. So let's talk about how we regulate these things. But let's first look at a graph where you can see the percentage above or below the national ambient air quality standards set by the EPA. And that's, as you go down, you have less and less of the pollutant. And you'll see that we have the year from 1990 to 2000, and then we have lead that has its own little axis here, because lead has been a big change. But you'll notice all these air pollutants have dramatically dropped since the 90s. Now, why is that? Well, we've enacted some pretty strict air quality rules that sometimes get weakened depending on the president in office. So, for instance, when Ronald Reagan was the president, he severely limited the Clean Air Act. When Donald Trump was the president, he severely weakened the Clean Air Act as well. So it depends on who's the president at the time. But generally speaking, the Clean Air Act of 1970 was a pretty awesome piece of legislation, because you can, again, see the effects of pollution declining dramatically over time. And I think lead is sort of the best example, because lead actually had two pieces of legislation, as you'll remember. You remember there was a piece of legislation in 1986 banning lead in gasoline, and we had this piece of legislation in 1970 also limiting lead as well. And you can see lead levels have dropped by well over 1,000%, again, relative to the standards in essentially a 25-year period. So our regulations have done pretty well to limit atmospheric pollution. Now, there's many things that constitute atmospheric pollution. We've talked about lead, we've talked about carbon monoxide, we talked about nitrogen oxides, we talked about ozone, but there's some, and sulfur dioxide, as well as particulate matters. So there are some primary and secondary pollutions, and what levels are acceptable, and how often you have to sort of meet the compliance standard set under the NAAQS, or the National Ambient Air Quality Standards. And so that's it's been good, right? So clearly the Clean Air Act of the 1970, the banning of lead in gasoline and paints was a good thing. But we actually had an enacting in 1975 of the Energy Policy and Conservation Act by the Department of Transportation, which actually aimed to set minimum MPG, or miles per gallon, standards for cars and vehicles. And we also know there's also the CAFE, or the CAF, or corporate average fuel economy standards set by corporations to limit their trucks and light trucks as well. And those have actually dramatically increased the miles per gallon. And you'll notice that all of these things can also be put in the air by cars, as well as combustion of any fossil fuel out there. So this was another important piece of legislation that helped improve our air quality. And in addition, we also saw in 1990, we added some amendments to the Clean Air Act, which allowed the capacity to trade emissions between companies, where the EPA basically said, here's the maximum emissions for a company from utilities, and then you can actually trade that to other companies for money. So if you're a company that does really good at not polluting, you can trade that to another company, get some cash out of it, and sort of operates under the U.S. cap and trade policies that we see. Now, the reality about our air pollution is that while there are national standards, certain states do a better job. Now, I'm going to give you a pretty good example of this. So we have Massachusetts. Now, for those of you that own a car, and you live in Massachusetts, you know every year you have to get your car inspected. It's a big pain in the butt. It costs you $35, but you have to do it. Now, why do you do that? Well, we do it because we make sure cars are safe. But the other thing we do here in Massachusetts is we actually make sure cars, both new and old, up to 25 years old, of course, don't exceed or don't pollute too much. So we have this strict policy here in Massachusetts to regulate air pollution. And one of the ways we do it, again, is by having our yearly car inspections to make sure your car is not polluting too much. So that's Massachusetts. Now, if we drive about 15 hours or about 900 miles over to our friends in Michigan, our friends in Michigan actually have some of the worst air quality in the entire country. It's just at the national standards. Now, why is that? Well, Michigan, as you guys probably know, is known for two things: producing cars, right, and industry. That's what Michigan is kind of known for, right? Factories and cars. And so because Michigan values those things so heavily for the economy, mostly in the past, but still to a pretty heavy extent today, they have very, very low air quality standard. So you can go to Michigan and you can see very poor air quality in the Detroit metropolitan area. And even though Detroit is a smaller city than Boston, Boston has way better air quality because Boston and the state of Massachusetts enforces much stricter air quality laws than the state of Michigan does. And I'll just mention one last thing. The state of Michigan also does not have any inspections on their cars. So you can drive around in Michigan every day with an uninspected car. And you can basically, I remember one time my wife and I were driving in Michigan, and again, because they don't have any car inspections, I saw somebody with their car on their back windshield was a piece of wood because they lost their back windshield. And inside the piece of wood, they had cut a hole in the piece of wood and put a piece of plexiglass in the piece of wood as their way to see out their back window. And then another time, my wife and I saw a car that had an air conditioner. I mean, like a window air conditioner in the windows of one of the cars, keeping the car cool during the summer. So really lackadaisical enforcement of air quality rules in Michigan, but also lack of inspection of cars leads to differential air quality within the country as a whole. So just as a cool little tidbit about how these things are enforced. Again, they're not equally enforced. They should be, and they should be much higher, but again, they're not always. So this leads us to our sort of final slide. I'm going to skip this one because we don't need to talk about what's going on in China. I think the examples I gave you for Massachusetts and Michigan are already sufficient. But the question is, what can you do as an individual? Well, most air pollution is produced via the combustion of fossil fuels. So the best way to sort of get around that is with cleaner vehicles, higher miles per gallon, getting your energy. So if you have the opportunity to, like for instance, in Massachusetts, you can get your energy from wind or solar power so that you're not getting your energy from the combustion of fossil fuels, i.e. making worse air quality conditions for you and your neighbors and things like that. So that's one way you can do it. But as with most things in this class, it really starts at the federal level. We should really at the federal level have some much stricter air quality rules so that places like Michigan don't sort of fall by the wayside with really poor air quality. And you might ask yourself, why does it matter if air quality is good? Well, as we'll discuss during climate change lecture, about 8 to 9 million people die every year globally because of poor air quality. So air pollution is bad for lots of environmental reasons, but it's also really bad for human life, right? One of the parts of the urban tax that we discussed in our previous lecture about urbanization is part of it is just the tax from pollution living in a city, right? And I meant tax isn't like taxing on your body, not taxing on your paycheck. And so urban pollution as a whole is really bad for human biology. So if you like people to not die prematurely from air pollution, definitely tell your congresswoman, congressmen, your senators, better, stricter air quality, air pollution controls. And that's going to be it for today's class. So I'm going to stop recording here. I'll hang around for a bit if you guys